How did the sun form from a cold, ancient cloud of gas and dust? What processes turned leftover material around the young sun into planets? In a quiet corner of the Milky Way galaxy, long before our sun ever began to shine, a vast cloud of gas and dust drifts in darkness. It has hung there for ages, uncounted, cold, just a few degrees above absolute zero, and utterly still, illuminated only by faint glimmers of distant stars. This cloud is one of many sprinkled throughout the galaxy, a gentle mist of cosmic material. In its heart, all is tranquil. No breeze stirs in the vacuum, and time itself seems frozen amid the floating motes. Yet something is different about this particular cloud. Something is about to change. Perhaps a distant star lived out its life and died in a fiery supernova, sending a ripple through the galaxy. Maybe that shockwave travelled light years, finally reaching this quiet cloud and giving it a subtle push. Or perhaps, by sheer chance, a denser patch formed in the cloud, a region just a bit heavier than its surroundings. Whatever the cause, a gentle imbalance tiptoes into this cloud's serenity. It is a poetic image. The death throes of a far-off star may have sparked the birth of our own. Even in the cold vacuum, cause and effect whisper across light years. Slowly, almost imperceptibly at first, the cloud begins to gather inward. Gravity has awoken. Tiny fragments of dust and gas feel an irresistible pull, drawn toward the growing dense patch. What was once diffuse and still now develops a center, a place where more and more matter collects. The cloud's quiet is replaced by a slow, inward motion. Over many thousands of years, this motion quickens. The gas and dust spiral inward, as if an invisible hand is sweeping them to the center of the cloud. As the cloud collapses, it starts to spin. At first, the rotation is barely a whisper, a gentle turning. But as the cloud grows smaller, it spins faster, like a skater pulling in her arms during a graceful pirouette. What was once a languid drift becomes a slow whirl. The material flattens into a broad disk, all swirling around a central point. And at that center, something new is forming, hidden within the thickening haze. The gas at the core is squeezed tighter and tighter by its own weight. Pressure builds. Temperatures climb in the heart of the collapsing cloud. The atoms in the gas begin colliding more fiercely, the very conditions for a great ignition slowly falling into place. Still, from outside, all remains dark. No star yet shines, just a dense, hot ball growing at the cloud's center, shrouded by whirling dust. Time stretches on. Piece by piece, the cloud's substance continues to rain into the center. The core grows massive, heavier and hotter, until the atoms within it are pressed and excited to an extreme. And then, at last, in an event both violent and gentle, light blossoms where there was none. Deep in the core of the forming protostar, hydrogen atoms begin to fuse into helium. A new light is born, a star's first breath. What was once a dark, cold expanse now has a beacon. Our sun has awakened. In that moment, the core of the cloud becomes a newborn star, its surface igniting in a brilliant glow. Starlight streams outwards, pushing back the darkness that had lasted for eons. The surrounding space, once black and silent, is now bathed in the gentle glow of a young sun rising for the very first time. In that first dawn of starlight, the surrounding cloud begins to respond. What had been invisible in the dark now glimmered softly. Dust motes and gas all around were bathed in the newborn sun's rays, creating a glowing halo in space. The swirling disk encircling the sun could now be seen as a bright band, as the light scattered off its tiny particles. It was a cosmic sunrise, not just for the sun, but for the materials that would soon become planets. Yet the sun is not alone in this new dawn. All around it, the remaining gas and dust that did not fall into the star are still there, circling. This leftover matter, spread out in a vast disk encircling the sun, holds the ingredients of worlds to come. And perhaps our sun was not truly alone in its birth. Stars often form in clusters, dozens or even hundreds igniting together from one vast cloud. In that distant dawn, our sun may have had sister stars sparkling nearby, all born from the same parent nebula. For a time, they would have been a family of suns drifting through space in unison. But as the eons passed, the cluster dissolved. Each young star gradually wandered off on its own path around the galaxy. The sun's siblings scattered into the Milky Way, and today our sun voyages seemingly alone with its planets. Somewhere out there, far across the stellar ocean, those long-lost sibling stars may still shine, carrying the same ancient heritage as our sun. The story of our solar system is only just beginning, with the sun's birth marking merely the first chapter of a much larger tale. In the wake of the sun's fiery birth, a broad disk of gas and dust remains in orbit around the young star. Bathed in the newborn sun's glow, this disk stretches wide and thin, like a great cosmic pancake spinning slowly in the void. Countless tiny particles, mote-like specks of rock and ice, dance within it, circling in endless loops. What was once a chaotic cloud has become an organized carousel, a flat plain of shimmering dust bathed in faint sunlight. Within this swirling disk, the seeds of planets are beginning to take root. From a distance, this disk might have resembled a glowing halo around the newborn sun. Up close, if one could journey through it, the scene would be otherworldly. Fine grains of dust would surround you like golden mist, illuminated by the sun's new light. Closer to the sun, the haze would grow thinner and the heat more intense. Farther out, the sunlight would dim, and the cold, dark stretches of the disk would feel almost like a starry night, with countless icy motes twinkling. It was within this subtle, spinning cloud that every planet, moon, asteroid, and comet in our solar system had its origins. Amid the dust and gas, change is afoot once more. Tiny grains of dust drift and occasionally meet. When two motes of dust bump ever so gently, they sometimes stick together, held by a fragile static pull. Bit by bit, these grains gather into larger clumps, like snowflakes accumulating in a quiet drift. No sound accompanies this assembly, just the silent, inexorable gathering of matter. From microscopic specks, little granules form, and those granules attract more, growing into pebbles that wander through the disk. As time flows on, the pebbles become stones, and the stones become boulders. In this vast protoplanetary sea, pieces of debris find each other and merge, drawn by the same force that pulled the great cloud inward: gravity. Most collisions are gentle, like soft touches, allowing the pieces to stick and slowly grow. Occasionally, a faster encounter shatters a clump apart, but even these fragments may later rejoin elsewhere. Little by little, the scattered building blocks are gathering into discernible bodies. In the silent darkness of the disk, countless nascent rocks are coming together, assembling the foundations of future worlds. Before long, some of these clusters of rock and dust reach sizes of kilometers across, or more. They are no longer mere pebbles or boulders, but miniature proto-worlds in their own right. These embryonic building blocks are called planetesimals. Each planetesimal wanders around the sun in the disk, pulling in smaller fragments with its growing gravity. When two planetesimals meet, they might smash violently or meld together, depending on the angle and speed of their encounter. Through countless mergers and occasional destructive impacts, the number of large bodies gradually shrinks, even as each surviving body grows in size. In time, a handful of these planetesimals swell into something greater. Protoplanets. These are massive enough to shape their surroundings. A protoplanet clears a path in the disk, sweeping up smaller debris in its orbital lane. In the inner regions closer to the Sun, dozens of these protoplanets take shape, ranging from the size of moons to perhaps as large as small planets. They move in graceful loops around the Sun, occasionally perturbing one another with their gravity. Each is hot from formation, its interior warmed by the energy of countless collisions. The young solar system is a crowded, dynamic place, with many fledgling worlds circling their star. This era of growth is as violent as it is creative. From time to time, two large protoplanets find themselves on a collision course. In those moments, two worlds may collide in a titanic impact, fusing into one larger body, or sometimes obliterating each other. The debris from such colossal crashes can rain down upon the surviving world, or scatter into space, only to be gathered up by another neighbor later on. Through this chaotic dance of creation and destruction, the population of protoplanets dwindles. What remains are fewer, larger worlds, each having claimed the materials of many smaller predecessors. Slowly, order begins to emerge from the frenzy. Not every nascent world survives this era. Some unlucky protoplanets are sent careening out of the solar system altogether, flung into the interstellar dark by gravitational encounters with the emerging giants. Others spiral inward and vanish into the sun, their material absorbed by the star they orbited. What ultimately remains is a select few planets on stable orbits, the survivors of a chaotic youth, destined to become the familiar worlds we know. Under the same sun, different fates await the worlds forming at different distances. Near the sun, the warmth is intense. Only substances that do not easily vaporize, metals and rocky minerals, can solidify so close to the star's heat. Lighter materials like ices and gases are driven away or remain vaporized in these inner zones. And so, the protoplanets growing near the sun are made of heavy, dense ingredients. They are destined to become smaller, solid planets built primarily of rock and metal. Their surfaces will one day be solid ground, and they will hold only thin blankets of gas, if any. Farther out, beyond an invisible boundary known as the frost line, where the sun's warmth grows weak enough that ices can survive, a different scene unfolds. Here in the chill of the outer disk, water can freeze into ice, and other compounds like methane and ammonia also condense into solid grains. These ices join the rocky debris, providing far more material for building planets. The young giants that grow in these cold reaches start as massive solid cores, much larger than any inner planet seed. Once a core becomes sufficiently heavy, it begins to draw in the surrounding hydrogen and helium gas from the nebula. They swell in size, cloaking themselves in thick blankets of gas. Thus are born the gas giants, enormous planets with dense cores and vast, swirling atmospheres. Among these distant giants, Jupiter and Saturn loom the largest, each wrapped in colossal hydrogen-rich skies and girdled by rings of dust and ice. Farther out still, Uranus and Neptune form as slightly smaller cousins, their atmospheres rich with water, methane, and other ices, giving them deep blue and green hues. All four of these outer planets are behemoths compared to the inner worlds, each a majestic presence in the young solar system, with moons forming around them like miniature systems of their own. In the end, this disk gives rise to a family of diverse worlds. Closer to the Sun, 4 small, dense planets will emerge, their surfaces solid and their atmospheres thin, the terrestrial planets. Far beyond them, 4 immense planets will dominate the outer reaches, composed mostly of gas and ices, the giants of our solar system. Each world follows its own path around the Sun, bound by the star's gravity and born from the same original cloud, yet each so different in character. Not all material finds its way into a planet. A great number of smaller remnants persist even after the major planets take shape. Between the orbits of the rocky new worlds and the mighty giants beyond, there lies a broad ring of debris, the asteroid belt. These asteroids are pieces of the solar nebula that never managed to form a planet, their growth stunted by the disruptive gravity of the giant Jupiter nearby. They remain as rocky reminders of the solar system's unfinished construction, orbiting the Sun in a broad band. Farther out beyond Neptune's realm, the Sun's influence still holds a distant repository of icy leftovers. In a region known as the Kuiper Belt, countless frozen bodies circle quietly in the dark. Some are small and comet-like. A few are sizable enough to be called dwarf planets, worlds of ice and rock. Beyond even that, astronomers believe an invisible halo of comets, called the Oort cloud, surrounds the solar system at its farthest edges. These remote icy wanderers usually slumber at the edge of space, but occasionally one is nudged from its orbit and begins a long fall toward the inner solar system. As it approaches the Sun, it springs to life as a glowing comet, trailing a luminous tail of vaporized ice and dust, a fleeting visitor from the solar system's frontier. As the Sun continues to shine and mature, its warm breath, the solar wind, begins to sweep through the system. This steady outflow of charged particles from the Sun acts like a cosmic breeze, blowing away the remaining thinner veil of gas in the disk. With the gas gone, the era of planet formation draws to a close. In cosmic terms, the architecture of the solar system was established quickly, likely within only tens of millions of years after the Sun's birth. What remains are the solid worlds and leftover debris that have already formed. The architecture of the solar system is largely set. A central sun encircled by planets large and small, along with belts of asteroids and distant reservoirs of comets. In the newfound clarity of a system without a thick disk, the young sun illuminates its new family, casting light on each nascent world as they continue to cool and settle from their turbulent births. Among these newborn planets is one we now call home, the Earth. At this early time, Earth is a molten, growing sphere, still taking shape under constant bombardment. It circles the sun amidst the remaining debris, its surface glowing red-hot from formation's heat. Yet Earth's story has a dramatic twist ahead. In the final stages of Earth's formation, an enormous collision waits on the horizon, one that will forever change Earth by giving it a moon. This is the next riddle in our cosmic tale, how a violent impact led to the serene beacon that graces Earth's night skies. In the tumultuous youth of the solar system, The newly formed Earth was a fiery, glowing sphere. Still recovering from its birth, the young Earth was molten at the surface, its air thick with fumes, and its landscape an ocean of magma. Even as it began to cool and solidify on the outside, space around it remained a shooting gallery of debris. Countless rocks and leftover fragments from planet formations still swarmed, occasionally striking the new planets in flashes of light and fury. It is in this chaotic setting that Earth's path was forever altered by a singular, titanic event. It was likely only a few tens of millions of years after Earth took shape that disaster struck. Among the wandering protoplanets was one perhaps the size of Mars, travelling a path that fatefully intersected Earth's. This rogue body, often called Theia, hurtled toward the Earth, drawn by gravity and chance alignment. In a silent instant, Theia and Earth met in a cataclysmic collision. One can imagine it in almost slow motion, two worlds merging in a blinding, soundless impact. The force of the collision was beyond comprehension. Earth's surface erupted, and both bodies' materials were flung into space, molten rock spraying out around the wreck of the impact. For a time, chaos reigned. The impact obliterated the smaller body and splashed a huge halo of debris into orbit around the shattered Earth. Mountains of vaporized rock and hot molten droplets arched out into space, caught by Earth's gravity. Our planet was left reeling. Earth itself nearly melted anew from the energy of the blow, its young surface turned back into glowing molten rock. Above this roiling Earth, a ring of incandescent debris formed, glowing red and orange as it cooled from white hot. It encircled Earth like a luminous band, the raw material from which a new celestial companion would emerge. For a brief cosmic instant, Earth may have resembled a fantastical vision, a red-hot globe surrounded by a fiery ring. In those moments after the impact, our planet looked like a miniature sun with a bright halo. The debris, ranging from tiny glowing droplets to mountain-sized chunks, orbited around the Earth, gradually spreading into a disk. It was a sight of both beauty and devastation, a temporary ring system born of violence, glowing against the darkness of space. Over the weeks and months that followed, the ring of debris began to clump together. Under the gentle tug of its own gravity, the orbiting rubble started to gather into larger pieces. Eventually, much of the debris coalesced into a single spherical body, the earliest form of our moon. At first, this newborn moon was a molten orb itself, a miniature world glowing faintly as it cooled and solidified. It circled very close to Earth, much closer than the moon we know today. From Earth's perspective, had there been an observer, the moon would have loomed enormous in the sky, a giant glowing ember hanging overhead. Earth and the moon were now bound in an orbital embrace. The Earth, still spinning rapidly from its formation and that colossal impact, showed the newborn moon a furious rotation. A day on Earth may have been only a few hours long at first. With the moon so near, its gravitational pull on Earth was immense. It raised enormous tides in the molten rock, and later in the oceans once they formed, pulling the very surface of Earth slightly toward it. This tidal interaction acted like a brake on Earth's spin over time, slowing our planet's rotation gradually. As it did so, it transferred that energy to the moon, pushing the moon farther away. Slowly, over millions and then billions of years, the moon drifted outward to a more distant orbit. A day on Earth that might have been 5 or 6 hours long in the beginning lengthened gradually into the 24-hour day we now find familiar. Even now, the moon drifts a little farther from Earth each year, just a few centimeters. But over eons, that subtle retreat will continue to slow Earth's rotation ever so slightly more. the presence of the moon became a stabilizing influence on the Earth. Our planet's axis, the imaginary line around which it spins, leans at an angle, giving us seasons. Without the moon's steadying gravitational pull, that tilt could have wobbled much more chaotically over time, leading to extreme climate swings. But with the moon's constant tug, Earth's tilt has remained relatively steady, ensuring a more stable climate through the ages. The daily rising and falling of the ocean tides are another gentle gift of the moon's gravity. As the moon pulls on Earth's oceans, it creates rhythmic motions of water that have echoed through billions of years, possibly aiding the early dance of life along ancient shorelines. The giant impact hypothesis, as this origin story is known, elegantly explains many features of the Earth and Moon. Yet some riddles remain. For instance, lunar rocks brought back by astronauts revealed that the Moon's composition is strikingly similar to Earth's mantle and crust, almost as if the Moon were made from Earth's own material. This makes sense if the debris came mostly from Earth during the impact, but it raises questions about what happened to the impacting body and how thoroughly it mixed with Earth. Moreover, the Moon is deficient in certain volatile elements and has a much smaller iron core than Earth, suggestive of the violent, high-temperature birth it experienced. Scientists continue to study these chemical clues to refine our understanding of that long-ago collision. Today, the Moon hangs in our night sky, serene and silvery, seemingly so distant from the violence of its birth. But every crater on its surface, every basalt plain, the dark lunar seas, offers whispers of its origins. It is a testament in rock to a time when worlds collided and reshaped each other. The quiet moon, governing our tides and lighting our nights, was born from chaos and fire. Its journey from incandescent debris to the gentle beacon we know is one of the great transformations in the story of our solar system. For countless generations, humans would gaze at the moon's gentle glow, spinning stories about gods and animals in its patterns, unaware of the true drama that formed it. Only in the last few decades, by travelling to the moon and examining its stones, did we confirm this story of a giant impact. The moon's rocks quietly recorded that ancient violence, and in studying them, we unravelled the tale of its birth out of chaos. With the moon's formation, Earth's violent adolescence began to calm. The Earth and Moon system cooled over time. A solid crust formed on Earth as the constant barrage of impacts slowed. Yet in those early days, any water that Earth might have had would have boiled away in the intense heat or been blasted off by impacts. As Earth started to settle down, it was essentially dry, a rocky world waiting for relief. The next puzzle was how this parched planet came to possess the vast oceans and rivers that we know today. To find the answer, we must turn to the icy messengers from the outer reaches of the solar system, the comets and water-rich asteroids that would deliver the gift of water to the young Earth. In the early epoch, as Earth cooled enough to form a solid crust, the planet remained dry and barren. But far out on the fringes of the young solar system, icy wanderers had been waiting since the beginning. Imagine one such distant body, part ice, part rock, knocked off its quiet course by a gravitational nudge. It begins a long, spiraling journey toward the sun. After millennia, gliding through cold space, this wanderer is drawn into the inner solar system, picking up speed as it approaches the warming glow of the sun. This is a comet, and it carries a precious cargo, water, frozen into ice deep within it. Eventually, the comet's path crosses that of Earth. With a final fatal plunge, it streaks into Earth's atmosphere as a brilliant fireball. In a flash, the comet collides with the surface. Much of the ice it carried vaporizes instantly from the heat of impact. Though the comet is destroyed, it leaves something behind. Its water vapor mixes into the atmosphere. In time, as the Earth cools further, that vapor can condense into liquid droplets. Rain begins to fall onto the cooling rocks below. What was once a dry world feels the first wet touch of water. Picture that first rain falling onto a barren world. At first, each drop might have sizzled into vapor upon touching the scorching surface. But as the Earth's crust cooled, the raindrops began to survive, pooling in low hollows. Steaming rainwater collected in the craters and basins left by earlier impacts. Clouds would have clung to the sky in a perpetual twilight, releasing torrential downpours that slowly filled the ancient depressions. It was a gentle but persistent transformation. Over time, dry land darkened with wetness, and the first temporary lakes glimmered under a hazy sky. It wasn't a single comet that gave Earth its oceans, but countless deliveries over many millions of years. Early Earth was bombarded by swarms of these comets, especially during the tail end of formation when debris still roamed abundantly. Each comet that struck released more water, a few drops added to the growing inventory. In addition to comets, many water-rich asteroids, chunks of rock from the cooler outer regions of the asteroid belt, also rained down. Some of these asteroids carried water bound up in minerals, which upon impact and heating could be freed as vapor. Together, these impacts slowly planted the seeds of Earth's future oceans. Scientists seeking to unravel the origin of Earth's water often turn to chemical clues. Water isn't exactly the same everywhere. It carries a subtle fingerprint in the ratio of certain forms of hydrogen. The water in Earth's oceans bears a resemblance to the water found in primitive asteroids, more than to that in many comets observed today. This suggests that water-rich asteroids may have played a particularly large role in wetting the Earth. However, some comets have been found with more Earth-like water as well, so the story is complex. The truth may be that both comets and asteroids contributed, in an uncertain combination that we are still working to understand. Indeed, some meteorites that fall to Earth even today, ancient fragments of water-rich asteroids, contain tiny amounts of water and carbon compounds. They offer a tangible clue that rocks from space have long carried the seeds of oceans, and perhaps even the precursors of life. As the relentless rain of cosmic ice continued, puddles formed on the cooling Earth. Those puddles joined into pools, and the pools grew into lakes and shallow seas. Over a very long time, as more water accumulated and the planet's surface reshaped itself, the first true oceans appeared. Imagine the once glowing red Earth now turning mottled blue and grey, steam rising from new-formed seas as rain clouds burst above. By perhaps a few 100 million years after the planet's formation, a significant portion of Earth's surface was covered in water. The dry rock had given way to oceans of liquid water, shimmering under a young sun. Water transformed the Earth. With it came the possibility for life as we know it. The oceans would become cradle and mirror, reflecting skies and nurturing simple organisms in the eons to come. Had those comets and asteroids not delivered their gifts, Earth might have remained a barren rock, just another dry world. Instead, our planet became a blue marble, distinguished by vast oceans. We have the cosmos to thank for this, the countless small emissaries that travelled across space to bring Earth what it lacked. And water was not the only gift delivered from the heavens. Along with the ice, those wayfaring comets and asteroids carried other treasures. Carbon-rich molecules, organic compounds, and minerals that would enrich Earth's surface. Each impact was like a small delivery of ingredients, seasoning the young Earth with the chemistry needed for life. So when the oceans eventually formed, they were not just filled with water, but also infused with a cosmic broth of elements, ready, in time, to brew life's first simple cells. Yet, mysteries remain in this tale of water's arrival. Exactly how much came from comets versus asteroids? Did some of Earth's water lurk inside from the very beginning, trapped in minerals and released by volcanic breath? We still seek these answers. In fact, minute mineral grains on Earth have hinted that liquid water existed surprisingly early, within just a few 100 million years of Earth's formation, adding to the intrigue. What is clear is that by the time Earth was a few 100 million years old, it had oceans. The stage was set for the next chapters in Earth's story, including the emergence of life. But before life arose, Earth and its neighboring worlds would endure an era of intense bombardment that would shape their surfaces forever. The scars from that violent time are still visible today, and they tell a story of their own. Interestingly, not all worlds were equally endowed with water. Closer to the Sun, tiny Mercury likely saw any water it had baked off by the relentless heat. Venus, too, probably began with some water, but it turned into a hothouse where oceans could not last, and the water escaped or was broken apart in the upper atmosphere. Mars, being smaller and farther out, received a share of water, and for a time had rivers and perhaps shallow seas. But it eventually lost most of it to space as its climate changed. Among the inner planets, Earth alone managed to retain vast oceans over billions of years. A fortunate outcome of just the right conditions and continued replenishment. Roughly 4 billion years ago, the solar system was beginning to settle, but it was not yet peaceful. During this ancient epoch, the inner planets endured an onslaught of impacts in what we now call the heavy bombardment. Countless asteroids and comets, destabilized from their orbits, came hurtling inward. Perhaps a subtle shift in the dance of the giant planets, or a passing resonance, sent these swarms on a collision course with the inner worlds. Some were as small as pebbles, burning up as shooting stars. Others were mountain-sized or larger, capable of carving out vast craters on any world unfortunate enough to lie in their path. For tens of millions of years, impacts were frequent and violent across the young solar system. Had there been eyes to gaze at the night sky during that era, they would have witnessed an unsettling spectacle. Meteors crisscrossed the heavens in great numbers, night after night, countless shooting stars streaking overhead. Every so often, a brilliant fireball would flare, outshining even the brightest stars, as a larger body tore through the atmosphere or smashed into a distant surface. Some impacts were so colossal that their flash could have been seen from neighboring worlds, momentarily turning the dark sky eerily bright. The inner solar system was alight with these fireworks of destruction, a fierce meteor shower that lasted not just hours or days, but millions of years. On Earth, each large impact was a cataclysm, blasting huge cavities in the ground, boiling oceans, and shrouding the globe in hot debris. If life had been trying to take hold during this era, these repeated hammer blows would have made it difficult for anything to survive on the surface. Yet Earth was resilient, and as time passed, the bombardment slowed. The evidence of those early impacts on our planet has largely vanished, erased by eons of wind, water, and the restless churning of Earth's crust. But elsewhere, the story of that violent time is written plainly on the surfaces of other worlds. The Moon, airless and geologically quiet, preserves the scars of the heavy bombardment like a cosmic archive. In that way, the moon stands as a silent chronicle of an era that Earth itself has forgotten. Gaze at the moon on a clear night, and you see a face mottled with countless craters. The lighter highland regions of the moon are saturated with overlapping craters from those ancient times, a record of near-endless battering. Even the darker patches, called Maria, once thought to be seas by early skywatchers, are actually enormous impact basins formed by gargantuan collisions. One such basin, Mare Imbrium, the Sea of Rains, stretches over 1,000 kilometers across, a scar from one of the last great impacts of the bombardment. In the aftermath of those basin-forming impacts, lava welled up from the moon's interior to fill the depressions, cooling into smooth plains. That's why the Maria have fewer craters on top of them. They represent slightly younger surfaces that partially reset the crater count. Each crater on the moon is like a timestamp of an impact event. By counting craters and noting which lie on top of others, scientists can piece together a timeline of which areas are older or younger. The more craters a region has, the older it generally is, much like an old painting pockmarked with many stains. In this way, craters act as a kind of clock. For example, the densely cratered highlands of the moon tell us they are the moon's oldest surfaces, dating back to the heavy bombardment era. Meanwhile, the smoother basalt plains, the Maria, have fewer craters, indicating they formed later, after the most intense barrage had subsided. Mercury, the innermost planet, also wears the memory of that turbulent time. Its surface, like the moon's, is heavily cratered and bears the marks of innumerable impacts. One of Mercury's largest scars, the Caloris Basin, was gouged out by a colossal impact, and is so vast that a ring of mountains rims its edge. Mars, too, has ancient cratered highlands in its southern hemisphere, remnants of bombardments from early on. Even some moons of the outer planets, like Jupiter's Callisto, carry densely cratered crusts that speak to an ancient barrage of impacts, reaching even the far reaches of the solar system. It's thought that these ancient impacts did more than scar the worlds. They also seeded them with riches, metals and minerals that were once buried deep in Earth's interior, or entirely absent near its surface, might have been replenished by this cosmic barrage. In fact, precious elements like gold and platinum found in Earth's crust today could be gifts from those final waves of asteroids that struck long ago, adding a sparkling coda to the age of bombardment. In the silence of airless moons and static worlds, these craters whisper of the solar system's fiery youth. They remind us that even the most tranquil-looking cosmic landscapes were forged in violence. Every pit and pockmark in the moon's face is a story. A sudden collision in the dark, an explosion that shook the ground, then eons of quiet. Standing in one of those great lunar craters, one would be surrounded by towering walls of rock that once flowed like liquid from the heat of impact, now frozen in time. Beneath your feet, the ground would be carpeted in fine grey dust left by countless meteor falls. The silence would be profound, broken only by the faint whisper of your own breath. Above, the sun would shine in a black sky, its light stark and unblinking, illuminating a landscape of desolation that time has transformed into a kind of stark beauty. From these battered surfaces, we have learned about the chaos of our system's early days. They tell us that the stability we enjoy now was hard-won, emerging only after a tempest of collisions ran its course. As the heavy bombardment tapered off, the solar system became a calmer place. Impacts still occurred now and then, but nothing on the scale of that early storm. This relative peace allowed planets like Earth to heal and life to eventually sprout in the quieter epochs that followed. But even in this relative calm, one actor remained capricious and powerful: the sun itself. Our star, though life-giving, has its own cycles and tempests. To truly understand the environment that shaped the planets, we must also look to the sun and uncover the enigmas of its behavior. In the sky, our sun appears as a constant, steady beacon, warm, life-giving, and unchanging from day to day. But behind this placid facade, the sun is a dynamic, sometimes turbulent star. Its bright face hides a deep complexity. Magnetic fields twist and coil beneath the surface, and gigantic streams of charged particles continually flow outward. The sun, in its own way, has weather and moods. Understanding the sun's temperament is key to understanding the environment of the entire solar system. One sign of the sun's changing moods can be seen even with modest telescopes: sunspots. These are dark, cooler patches on the sun's surface, some of them so wide that several Earths could fit across one. They come and go in cycles. Every 11 years or so, the sun moves from a calm phase to a restless peak and back again. At the height of its cycle, dozens of sunspots may freckle the solar disk, and the sun is often more active. During quieter times, few, if any, sunspots are visible. This rise and fall is known as the solar cycle, a kind of heartbeat of our star. When the sun is in its active phase, its magnetic fields can become tangled and strong. Sometimes these stressed magnetic fields suddenly snap and realign, unleashing tremendous energy. When that happens, the sun emits what we call solar flares, intense bursts of radiation and light. At times, these eruptions are accompanied by coronal mass ejections, where great billows of charged particles are hurled into space. Such events are the solar storms of our star, and when they sweep past Earth, they can stir our planet's magnetic field, igniting shimmering auroras near the poles. Even on calmer days, one can sometimes witness enormous loops of plasma, prominences, arching above the sun's limb. These graceful structures, held aloft by magnetic fields, can persist for days, towering many times taller than the Earth, before collapsing back into the star. If you've ever watched the aurora borealis or australis, the northern or southern lights, you've seen the Earth's own atmosphere responding to the sun's temperament. During a strong solar storm, particles from the sun rain into Earth's upper atmosphere, exciting the air molecules and causing them to glow in sheets of green, purple, and red. These ethereal lights dance slowly across the sky, a beautiful reminder of our connection to our star's moods. To the ancients, such lights were mysterious and magical. Today we know they are one of the sun's gentle whispers after a magnetic tempest. Even when not flaring dramatically, the sun is always emitting a steady stream of charged particles, known as the solar wind. This wind streams out in all directions, bathing the planets. It's a very thin gust of matter, but it fills the vast expanse of space around the sun, creating an invisible bubble called the heliosphere that encompasses all the planets. Within this bubble, the solar wind shapes planetary atmospheres and carves tails from comets. It is as if the sun's breath reaches out across the solar system, gently but persistently. Far beyond Pluto's orbit, at the very edge of this heliosphere, the solar wind finally meets the vastness of interstellar space. Remarkably, a pair of human-made spacecraft, the Voyager probes, have sailed through this boundary, leaving our sun's protective bubble behind. Now, as they drift in the silent space between the stars, they carry with them a piece of our sun's story, whispering it into the endless night. Yet, among all these phenomena, one of the sun's most baffling traits lies in its outer atmosphere. As we move outward from the sun's core to its surface, the temperature drops, as one would expect when going from a hot furnace outward. The visible surface of the sun, the part we see, is about 5,500 degrees Celsius, a searing but understandable heat for a star. However, high above that surface, in the sun's corona, the tenuous outer atmosphere that becomes visible as a pearly white crown during a total solar eclipse, the temperature soars to extraordinary levels, in the millions of degrees. This defies intuition. One would think things should get cooler farther from the core. But here it's the opposite. The corona is mysteriously, incredibly hot. Scientists have puzzled over this coronal heating mystery for decades. How can the sun's outer atmosphere be hundreds of times hotter than the layers below? The answer seems to lie in the sun's magnetic personality. The sun's surface is threaded with magnetic fields, like invisible strings of energy. Sometimes these magnetic field lines whip and oscillate, sending waves of energy upward. In other cases, they break and reconnect explosively in countless tiny bursts. Both of these processes, magnetic waves and microflares, are possible explanations, injecting energy that heats the corona to its astonishing temperature. Bit by bit, observations and experiments are providing clues, but the full explanation remains an active area of research. To uncover secrets like these, humanity has begun reaching out to the sun more directly. NASA's Parker Solar Probe, for instance, has been swooping closer to the sun than any spacecraft before, sampling the solar wind and measuring the corona's environment. Each pass brings new data, hinting at how energy courses through the sun's atmosphere. The probe has detected rogue waves and sudden spikes of heat in the solar wind, pieces of the larger puzzle of coronal heating. Such missions carry our curiosity right into the sun's domain, where we can almost touch the star's fiery breath. The sun's temperament also changes over far longer periods than human lifetimes. In its youth, the sun was likely more tempestuous, spinning faster and unleashing more frequent flares. Over billions of years, it has gradually calmed and even grown slightly brighter. In fact, the young sun shone far less fiercely than it does now, yet early Earth somehow stayed warm, a lingering puzzle known as the faint young sun paradox. In the very distant future, the sun will change even more dramatically as it runs low on fuel, swelling into a red giant and altering the solar system in profound ways. But for now, we live in a time of relative stability, where the sun's 11-year pulse and occasional storms are the rhythms we know. Despite all we have learned, the sun still holds mysteries that intrigue and humble us. We depend on its steady light and warmth every moment of every day. Thankfully, our sun is relatively calm for a star of its kind. Its stability over billions of years has given life on Earth a chance to thrive. Yet its inner workings and outer quirks remind us that even our familiar star has secrets. From the unexpected heat of its corona to the clockwork of its cycles, the sun is a living laboratory of physics that we are only beginning to fully grasp. It is a star, like billions of others in the galaxy, and yet to us, it is unique. Our sun, the anchor of our solar system, and the sustainer of life on Earth. Our journey through the early mysteries of the solar system, from the birth of the sun to the rise of planets, the formation of the moon, the coming of water, and the scars of ancient bombardment, has revealed a saga of creation and transformation. But the story is far from over. Even the planets that seem familiar to us are filled with marvels to explore. The inner planets each carry secrets in their stones and skies. Mercury, closest to the Sun, is a cratered furnace world that challenges ideas of how a planet so small could have such a large iron heart. Venus, eternally cloaked in thick clouds, swelters under a greenhouse haze and spins slowly backward compared to the others. Mars, cold and red, shows signs it was once wet and perhaps hospitable, raising questions about its past and whether it ever hosted life. Then come the giants. Jupiter, king of planets, with its restless great red spot storm and a family of intriguing moons. Saturn, adorned with majestic rings that whisper of shattered moons or leftover ice. Uranus and Neptune, the ice giants, tipped askew and distant, with mysteries of wind and weather in the far twilight of the sun. From the scorched surface of Mercury to the frigid twilight at Neptune's edge, each world invites us to wonder. As we continue our exploration, we venture outward, ready to uncover the next chapters of the solar system's grand enigma. Each planet and moon holds its own secrets, and our journey onward will delve into the enigmas of those far-flung worlds that orbit our sun. Now, as we draw closer to the sun, we encounter the first of the inner worlds, Mercury. Under the blinding glare of the sun, a tiny world spins in silence. Mercury, the innermost planet, endures extremes beyond imagining. Daylight brings furnace-like heat that bakes the rocky ground, while night plunges everything into bitter cold. Mercury rotates so slowly that daylight lasts for months beneath a sun that barely moves in the sky. When darkness finally comes, it persists just as long, allowing heat to radiate away into space and draping the land in deep freeze. No air softens these changes. Mercury's surface feels the full fury and the profound quiet of space. Mercury has an odd rhythm to its days and years. The little planet spins slowly, only 3 rotations every 2 of its years, creating a situation where one Mercury day lasts about 176 Earth days. That means if you stood on Mercury, the sun would take nearly 6 Earth months to glide from one sunrise to the next. Under such a relentless day, the rocks bake and crack, and then endure equally long nights of deep freeze. This sluggish spin is why Mercury's extremes are so intense. Half a year of sunlight, half a year of night, and no atmosphere to carry heat from one side to the other. To ancient sky watchers, Mercury was a fleeting wanderer, visible only at dawn or dusk, and never roaming far from the sun. The Romans named it after the swift messenger of the gods, because it appeared to hurry across the twilight sky. In reality, Mercury does race around the sun faster than any other planet, completing a year in just 88 Earth days. But up close, on its surface, there is nothing swift about Mercury's environment. It is timeless and still, a world holding its breath under the sun's glare. Despite its inhospitable face, Mercury holds mysteries that beckon exploration. Only 2 spacecraft have ever visited, Mariner 10 in the 1970s and Messenger in the 2010s. Each revealed a bit more of Mercury's story. Soon, a new mission, Bepi Colombo, a joint venture of Europe and Japan, will arrive to map Mercury in unprecedented detail and perhaps catch signs of ongoing changes. Scientists hope to learn more about those bright hollows and the ice hidden in shadow, and to understand how Mercury's enormous metal core shaped such a small world. In the meantime, Mercury spins on in isolation, a charred and frosty enigma that challenges our understanding of what a planet can endure. On this scorched and airless globe, time has etched peculiar stories into the terrain. Vast cliffs curve across the landscape, as if the planet's face has wrinkled over ages. These great ridges and scarps rise out of craters and plains, testaments to a world that has literally shrunk in on itself. As Mercury's hot interior slowly cooled long ago, its sphere contracted. The crust crumpled and broke, one section thrust over another, and immense cliffs were uplifted. They snake for hundreds of kilometers, looming high above the surrounding plains, frozen evidence that Mercury became a little smaller as the eons passed. Across these ancient highlands and basins, another quiet mystery glistens in the sunlight. Scattered on some crater floors are patches of strange brightness, like frost gleaming on dark rock. But it is far too hot for frost here. Closer inspection reveals shallow, rimless pits clustered together, hollows that pockmark Mercury's surface with a curious beauty. The hollows hint at something unexpected. Mercury, for all its heat, held onto volatile ingredients that are now disappearing. Scientists believe these bright depressions formed by the loss of materials that turn to vapor under Mercury's brutal conditions. Perhaps long ago, comet impacts or Mercury's own chemistry left sulfur or other unstable minerals mixed into the rocks. Now, so near to the sun, those ingredients literally boil out of the ground in slow motion. With no atmosphere to contain them, they sublimate into space, leaving the rock weakened and crumbling. The surface then collapses into voids where the volatile substance used to be, creating hollows that widen over time. What makes Mercury's hollows even more intriguing is their youth. The planet's surface is scarred with craters billions of years old, yet the hollows look fresh and bright, as though etched only yesterday on this ancient canvas. In fact, they may still be forming today. Mercury was once thought to be geologically long dead, a relic world changed only by meteor impacts. But the presence of these shiny hollows, likely only tens of thousands of years old, suggests that Mercury's skin is still subtly changing. Even in the absence of wind or water, the planet's very minerals are evaporating away under the sun's glare, reshaping the surface in our current era. Imagine standing at the edge of one of these hollows in Mercury's perpetual silence. The ground beneath your feet would be brittle and scorched. All around, a great basin wall rises, and the stars hang in a black daytime sky near the blinding sun. At your feet, the hollow gleams with a powdery light-coloured dust, the remains of vanished rock. In the distance, a massive cliff, one of Mercury's giant scarps, cuts across the horizon, casting a long shadow. That cliff was lifted up eons ago when the planet's shrinking interior wrinkled its crust. Together, the scarps and hollows tell a story of a little world still cooling and cracking, still shedding parts of itself to space. Mercury offers no easy clues to an observer. Much of its surface remains to be seen in detail. The hollows discovered seem unique in the solar system. Nothing quite like them has been found on the Moon or Mars. And those great thrust fault cliffs, they dwarf similar features on the Moon. Mercury's small size hides an oversized iron heart and a history of intense inner change. In the twilight along Mercury's terminator, the line between day and night, cold darkness creeps over land that was glowing hot just hours before. One might imagine that in these cooling hours, the ground quietly contracts a little more, perhaps hastening the formation of another tiny hollow. It is a slow, somber activity, utterly imperceptible in a human lifetime. Yet over geologic time, the cumulative effect has reshaped the planet. Mercury has shrunk by several kilometers in radius since its youth, and it continues to do so, ever so slightly today. Its surface bears the wrinkles of this gradual collapse, frozen in towering ridges. This airless world, closest to the sun is a place of paradox. It is blasted by the sun's energy, yet locked in deep freeze each night. In fact, Mercury even harbours water ice in the dark recesses of polar craters where sunlight never reaches. A frost preserved in a furnace, surviving only in eternal shadow. It is a landscape of stillness, yet not entirely still. It contracts, it crumbles, it surprises. In bright hollows and winding scarps, Mercury quietly discloses the remnants of its inner life. These enigmas of a shrinking globe and vanishing volatiles invite us to wonder what secrets lie in the sunlight and shadows of this little planet's face. Under the heavy glare and in the silent vacuum, Mercury keeps its quiet mysteries well, waiting for the next messenger from Earth to uncover more. Beneath an eternal blanket of cloud lies a world of crushing heat. Venus, second planet from the Sun, wears a brilliant white veil of reflective clouds that hide a tortured landscape below. In the glare of the sun, those clouds shine brightly from afar, making Venus a jewel in Earth's sky. But underneath them, the atmosphere is a cauldron. The air is almost pure carbon dioxide, so thick that it weighs down with a pressure over 90 times that of Earth's atmosphere. The surface temperature soars above 450 degrees, hot enough to melt lead. In this inferno, no water can exist. Any rain of sulfuric acid from the clouds sizzles into vapor before touching the ground. Daylight on Venus is a dim orange haze filtering through the clouds, and the terrain is a silent oven of rock and toxic gas. In fact, a single day-night cycle on Venus lasts longer than a Venusian year. The planet rotates so slowly and in the opposite direction of its orbit that the sun would appear to rise in the west and set in the east, if one could see the sun at all through the perpetual cloud deck. On the ground, the concept of sunrise or sunset is lost. It is always a stifled, murky daylight filtering down. When humans first attempted to visit Venus's surface with robotic probes, the planet's ferocity became evident. Several Soviet Venera landers in the 1970s managed to touch down on the Venusian plains, but even their sturdy engineering succumbed after an hour or two. In those brief moments, they sent back the only images we have from the surface: a haunting expanse of cracked, paver-like rocks stretching under a sulphurous orange sky. No signs of life or water, only a silent, oven-hot desert. Those landers confirmed what we had suspected. Venus's surface is truly as hellish as its climate, and any machine or person that visits can survive only minutes without extraordinary protection. Yet, scientists believe that Venus was not always such a hellish place. In the young solar system, Venus might have been far more temperate, possibly even hosting shallow seas and a gentler climate. With a size and gravity similar to Earth's, it's tantalizing to imagine that Venus once had blue oceans and clouded skies more like our own. If so, those oceans are long gone now, vanished into space or baked into the bone-dry ground. What happened? Venus took a different path, one of runaway warmth that transformed it completely. As the sun's energy beat down, Venus's water began to evaporate into the atmosphere. Water vapor is a powerful greenhouse gas, trapping heat. In a relentless cycle, more heat led to more evaporation, which led to even more heat. Eventually, the planet's oceans, if they existed, would have boiled away entirely. High in the atmosphere, the water molecules were torn apart by the sun's radiation. The light hydrogen atoms escaped to space, and oxygen likely reacted with the surface, or was lost as well. Carbon dioxide, released from rocks by intense heat, built up sky high. A thick, choking blanket of CO2 now trapped nearly all the sun's heat. This was the runaway greenhouse effect, a warming feedback loop that left Venus cooking under dense clouds. The result is the Venus we know today, a world where a lead bar would melt like wax on the ground, where the air itself is a heavy, stifling fog of heat. Across Venus's surface, much of the terrain is relatively smooth volcanic plain, vast fields of solidified lava stretching beyond the horizon in many regions. But rising above these plains are mysterious highland areas known as tesserae. These are plateau-like lands, crumpled and ridged in a complex patchwork pattern. Tessera highlands are among the oldest surfaces on Venus, bearing scars of intense deformation. In radar images that pierce the clouds, the tessera terrain looks like a lattice of overlapping ridges and valleys, as if great pieces of Venus's crust were shattered and jumbled long ago. Some scientists speculate that these highlands might be Venus's version of continents. Perhaps they formed when the planet's crust cooled and thickened in the presence of ancient oceans, or through a kind of tectonic process that has since ceased. The tesserae stand as time-worn islands of rugged terrain amid younger lava plains, holding secrets of Venus's distant past. They hint that the planet's history was more complicated, that in its youth, Venus might have had forces shaping its surface somewhat akin to Earth's crustal movements. The rest of Venus's visage also speaks to a dramatic story. Unlike the Moon or Mercury, Venus has surprisingly few craters. Almost the entire surface appears to have been repaved by volcanic activity on a global scale. Scientists estimate that about 500 million years ago, give or take, Venus underwent a kind of planetary renewal, an episode when volcanoes flooded the surface with lava, burying nearly all older terrain, except perhaps the Tessera highlands. Why this happened is another puzzle. Did internal heat build up under a stagnant crust until it burst forth everywhere, resurfacing the planet? Or has Venus been resurfacing gradually, and we just see the latest phase? In either case, Venus is a world dominated by volcanism. Countless volcanic domes, vast lava flows, and caldera depressions dot the landscape. The largest volcanoes, like the massive Mont Mons, rise kilometers high, though none pierce the perpetual clouds. One can imagine the ground of Venus as a rolling volcanic plain, molded by many eruptions over millions of years, a planet's surface continually remade by fire. But are those volcanoes still active today? For a long time, this has been one of Venus's great riddles. From orbit, our view is limited to radar and infrared glimpses through the clouds. In this indirect view, scientists have caught hints that Venus is still geologically alive. Sulfur dioxide gas in the upper atmosphere rises and falls in cycles, as if belched out episodically by volcanoes below. Infrared sensors have seen patches of the surface that glow slightly hotter than their surroundings, suggestive of fresh lava flows still cooling. And the clearest clue came when researchers compared radar images taken by an orbiter only months apart. One volcano's summit vent had changed shape and grown larger, strongly indicating that an eruption occurred in the interim. This discovery, decades after the fact, revealed that at least one Venusian volcano was active in the very recent past. It is likely not alone. Most experts now suspect that Venus, beneath its cloud veil, continues to rumble and ooze with ongoing eruptions. We just have not witnessed them directly. Imagine standing on that surface, an almost impossible feat. The landscape around you would be shrouded in a dense, yellowish fog of cloud-filtered light. The horizon might be difficult to see clearly, fading into a hot mist. You would stand on cracked black volcanic rocks, perhaps next to a sharp drop-off of a collapsed lava tube, or the strange fractured ground of a tessera highland. The air would press on you like an ocean overhead, and everything would feel eerily still. No breeze, just the thick air hugging every contour of the land. In the distance, maybe a cliff or ridge from a tessera plateau rises, its shape blurred by the heavy atmosphere. Above, the sky isn't blue, but a dull orange glow, and the sun is completely hidden behind perpetual clouds. On the ground, if you could survive, you might see the rocks softly radiating heat. It is a vision of a world where water once might have lapped the shore of ancient rocks, but now only parched stone and baking heat remain. Venus, in its silence, offers a sobering mystery. How a twin of Earth in size could follow such a divergent path. Its vanished seas, if they ever existed, left barely a trace. Perhaps only a faint chemical ghost in the atmosphere from water long lost. Its highlands hold clues of an earlier era that we have yet to decipher. And even now, behind the clouds, the planet may be reshaping itself with volcanic fire. In the thick air of Venus, we find both a mirror of Earth's potential fate and an enigma of a world that is fiercely alive, yet utterly inhospitable. That brilliant evening star hides a tale of transformation, one still unfolding in smouldering mountains beneath the clouds, and in questions scientists yearn to answer about our sister worlds past. Ever since humans first peered at Mars through telescopes, we have noticed the planet's appearance subtly changing with the seasons. For centuries, observers saw a reddish globe with white caps at its poles and darker patches that seemed to expand and contract over the Martian year. In the 19th century, some even imagined those dark areas were vegetation blooming during a Martian spring and fading in autumn. We now know they were mistaken. Mars is a cold desert, not a garden. Yet the red planet does have its own seasonal rhythms. Its face truly does shift, whispering clues about ephemeral processes at work in its thin air and barren ground. As spring comes to a Martian hemisphere, the brilliant white polar cap of winter begins to retreat. Mars has two kinds of ice at its poles: a seasonal cap of frozen carbon dioxide that waxes and wanes with the seasons, and a base of water ice that endures year-round. In winter, carbon dioxide from the atmosphere freezes out onto the pole, forming a broad cap of dry ice. When sunlight returns in spring, that dry ice sublimates directly back into gas, and the bright seasonal frost shrinks. From afar, you can literally see the polar cap dwindling, a shining white patch contracting as darkness gives way to sunlight. In tandem, pressure in Mars's atmosphere rises slightly as the vaporized CO2 returns to the air. Then, in the opposite hemisphere, autumn's cold will cause carbon dioxide to freeze out again as frost, and a thin hood of cloud will form over the growing polar cap. Mars breathes in and out, a ghost of its former atmosphere, with each turn of the seasons. Elsewhere on the planet, other changes paint the Martian surface anew. Those dark markings that perplexed early astronomers are not fields of vegetation at all, but vast expanses of rock and dust. In the wake of winter, winds stir and thin sheets of seasonal dry ice on the ground may crack and release jets of gas, kicking up dust in fan-like patterns on the slopes. As breezes gust across the rusty regolith, they erase old dust deposits and uncover darker basaltic sands beneath, temporarily darkening patches of the surface. Later, new dust will settle and lighten those areas again. This ebb and flow of dust can create the illusion of terrain shifting hue over time. Indeed, Mars is often wrapped in dust, sometimes in localized storms that appear as tan clouds, and occasionally in rare global dust storms that enshroud the entire planet. During such a global tempest, sunlight is dimmed to almost nothing at the surface, and from space, Mars becomes a featureless pale orb, until the dust finally settles. These storms can last for weeks or months, reshaping dunes and laying down new coats of powder across vast regions. When the skies clear, familiar craters and dark volcanic plains re-emerge, though often softened in tone, as if Mars has subtly changed face once again. Even on calm days, local winds can stir up trouble. NASA rovers have witnessed dust devils, spinning columns of dust, whirling across the Martian plains under the midday sun, momentarily carving dark tracks in the red soil as they suck up the bright dust. These brief dances of wind are like tiny whispers of activity on an otherwise quiet stage. Yet even in calmer times, Mars's atmosphere carries delicate whispers of change. Though far thinner than Earth's, it still transports slender clouds of ice crystals that can collect around Martian volcanoes, or drift as hazy streaks at dawn and dusk. In the early morning, one might see a faint, bluish-white cloud bank hugging the flank of Olympus Mons, the tallest volcano, as the night's chill causes moisture to condense. Come daytime, those wisps evaporate under the sun's rays. High above, fleeting clouds sometimes streak across the sky, casting brief shadows on the ruddy ground below. And in winter, spiral-shaped swirls of cloud can form over the poles, like tiny cyclones pinwheeling around the frost cap. These phenomena are subtle. One must watch closely to notice them at all. But they remind us that Mars, though cold and dry, still has an active sky on a human timescale, alive with the movement of air and ice. On the surface itself, the red planet holds other seasonal mysteries. Each year when temperatures peak, strange dark streaks appear on steep, sun-facing slopes, then fade as the weather grows colder. These are the recurring slope lineae, narrow lines that extend downhill during the warmer months. At first, scientists excitedly wondered if they were caused by salty liquid water seeping out from just beneath the surface, dampening and darkening the soil as it trickled a few hundred meters. It was a tantalizing idea. Even today, could there be trickles of water running down some Martian hillsides in the heat of summer? However, later evidence suggested a drier explanation. It may be that these streaks are simply dust avalanches, the sun's warmth destabilizing the slope just enough to send fine grains sliding and expose a darker layer beneath. When winter comes, the process stops, and the dark marks slowly fade or are covered by new dust, ready to form again when the next spring arrives. Whether wet or dry in origin, these seasonal slope markings remain a topic of lively debate, emblematic of Mars's habit of hinting at activity just at the edge of perception. Perhaps the most provocative whispers from Mars's thin sky are not visible at all, but detected by sensitive instruments. Over the past decades, robotic explorers have occasionally sniffed a whiff of methane gas in the Martian air, a gas that, on Earth, is often a byproduct of life or of certain geologic reactions. On Mars, the methane appears in tiny bursts. One rover's laser spectrometer measured a sudden spike of methane one summer night in Gale Crater, only for the gas to disperse days later. Orbiters looking from above have generally found the atmosphere to be virtually methane-free, adding to the puzzle. If these detections are real, what could be releasing the gas? One possibility is geological activity. For instance, chemical reactions between water and certain rocks could produce methane underground, which then leaks out occasionally. Another, more tantalizing possibility is microbial life below the surface, quietly breathing out this gas. Yet the inconsistent measurements have left scientists scratching their heads. Some teams even propose that the methane might be broken apart by Mars's sunlight, or absorbed by the soil almost as quickly as it emerges, which could explain why orbiting spacecraft see so little. For now, the existence of methane on Mars, and its source, remains an enigma. We catch only ghostly traces that vanish almost as soon as they're observed, like a faint scent on the wind. All of these subtle signs, the waxing and waning of polar ice, the dance of dust and cloud, the cryptic slope streaks, and the vanishing whiffs of methane, paint a picture of a planet that is not dead, but quietly dynamic. Mars today is no Eden. Its rivers and lakes dried up billions of years ago, and its air is achingly thin. The landscape we see is largely unchanging rock and dust under a salmon sky. Yet, if one watches patiently, Mars offers gentle reminders that it still changes with the seasons. A frost recedes, a dust cloud swirls, a dark slope stain creeps downward, and then fades. These are the soft voices of a world long past its prime, suggesting that even in dormancy, there is a kind of life. Not life as organisms, perhaps, but the living processes of a planet that still breathes, moves, and responds in small ways to the turning of the sun. Mars's face is indeed shifting, ever so slightly, beckoning us to keep looking and keep wondering at what we might see next. Today, Mars stands unprotected beneath the solar wind. Unlike Earth, which wears an invisible magnetic armor, Mars has no global shield to deflect the charged particles streaming out from the sun. Instead, those particles crash directly into Mars's upper atmosphere, gradually whittling it away. If you were on the Martian surface, you would be bathed in radiation that on Earth is largely fended off by our planet's magnetic field. Mars's sky is exposed, and this exposure has changed the planet's fate. But long ago, Mars did have a magnetic field. Billions of years in the past, the Martian core churned with molten iron and generated a protective bubble around the planet, just as Earth's core does today. We see hints of that ancient shield frozen in the rocks. Orbiters have detected strips of magnetized crust in Mars's southern highlands, remnant magnetism locked into rocks from an era when the planet's field was strong. Back then, Mars was a different world. A thick atmosphere of carbon dioxide blanketed the sky, and liquid water flowed in rivers and pooled in lakes. With a magnetic field in place, Mars could hold on to its air and water more easily, sheltered from the sun's harsh outflow. Something changed, however, and Mars's magnetic dynamo faltered. Perhaps the small planet's interior cooled to the point where its molten core couldn't sustain the churning motion needed for a magnetic field. Or maybe a colossal impact, or series of impacts, disrupted the dynamo early in Mars's history. Whatever the cause, by roughly 4 billion years ago, Mars's global magnetic field faded away. The invisible shield dropped, and Mars began to lose its protection. Over eons, the solar wind, a stream of high-speed charged particles from the sun, stripped the atmosphere, atom by atom. Lighter gases like hydrogen from water molecules were knocked free and lost to space. Gradually, the air thinned from a dense blanket to the tenuous wisps we find today. As the atmosphere bled away, the planet could no longer keep water liquid on its surface. Any lakes or rivers began to evaporate or freeze. The climate grew colder and drier. The evidence of this transformation is carved into Mars's features. Broad, dried-up river valleys, lake beds with cracked clay, and minerals that only form in water, all dating back to around the time the shield was lost. It appears that Mars went from a wetter, warmer realm to a barren one in geologic short order. Time, in a sense, sped up for Mars's habitability. The window for life, or Earth-like conditions, snapped shut far earlier on Mars than it did on our own planet. While Earth enjoyed billions more years of a stable, life-friendly climate under the guard of its magnetic field, Mars's hospitable era may have been brief and precarious. Even today, the loss of Mars's atmosphere continues. NASA's MAVEN orbiter has measured particles escaping to space, carried off by solar wind electric fields. In effect, Mars has a tenuous atmospheric tail streaming away into the darkness, like an invisible comet. What was once a thick blanket of air has been reduced to a thin veil that the sun is steadily peeling off. MAVEN has witnessed auroras dancing not just near the poles, but across the Martian sky. Auroras formed when energetic solar particles slam directly into the atmosphere, since Mars lacks a global field to funnel them toward the poles as on Earth. These auroras are invisible to human eyes and ultra-faint, but they are a sign that the solar wind is constantly colliding with Mars. During particularly intense solar storms, the rate of atmospheric erosion spikes, as if the sun is gusting away what little remains of Mars's once thick air. Without a magnetic field, Mars has also lost the luxury of a radiation shield over its surface. Cosmic rays and solar ultraviolet pour down unhindered. Any life on the surface would be hard-pressed to survive those conditions today. Life, if it exists on Mars now, might persist only underground or in rare protected niches. In a way, Mars's missing shield reshaped not only the planet's history, but its very prospects for life. Any potential Martian biosphere had to adapt quickly or disappear as conditions deteriorated. The story of Mars's lost shield is a cautionary tale of planetary change. It underscores how vital a magnetic field can be in preserving a planet's atmosphere and water. When the shield was strong, Mars was able to sustain rivers and a thicker air. When it vanished, the planet's water and sky were stripped away to a fraction of their former abundance. Now Mars is a dry, cold world, carrying the scars of that great loss. Its once flowing rivers are long gone, its atmosphere a thin ghost, and its deserts lie exposed to the harshness of space. And yet, locked within Mars's silent rocks, the imprint of an ancient magnetic field still lingers, a memory of a time when the planet fought against the void. It reminds us that worlds can change, that a planet's present desolation may hide a past that was warmer, wetter, and shielded from the ravages of space. Mars, without its shield, offers a glimpse of how different a planet's fate can be when protective forces fade and time takes a different course. Two small moons haunt the skies of Mars, racing silently around the planet. They are Phobos and Deimos, named for the ancient gods of fear and dread, fitting companions for the red planet's lonely orbit. Unlike our moon, these Martian moons are tiny and irregularly shaped, looking more like captured asteroids than the spherical worlds we usually imagine as moons. Phobos, the larger of the two, is a lumpy rock about 22 kilometers across at its widest, pockmarked by craters and etched with mysterious grooves. One face of Phobos is dominated by a gaping crater named Stickney, a scar from an ancient impact that nearly shattered the moon. That colossal blow may be what fractured Phobos and created the long grooves that scratch its surface. Deimos is even smaller, only 12 kilometers in size, a dark potato-shaped object. They reflect little sunlight, ashen grey in colour, blending into the blackness of space. Ever since their discovery in 1877 by astronomer Asaph Hall, the origin of Mars's moons has been debated. Are they wayward asteroids, snared by Mars's gravity eons ago? or remnants of a larger moon that broke apart, or debris from a colossal impact that struck Mars. The capture theory seems natural at first glance. Phobos and Deimos certainly resemble the carbon-rich primitive asteroids of the outer asteroid belt. Their composition appears to be carbonaceous, and their surfaces are dusty and dark, much like asteroid material. But there are puzzles with the capture idea. Both moons circle Mars in very circular, near equatorial orbits, which is unusual for captured objects, which typically approach on eccentric, inclined paths. Capturing an asteroid into such a neat orbit likely would have required some kind of drag or a thicker atmosphere to slow it down, and Mars's present atmosphere is far too thin. This has led some scientists to propose that the moons were born from Mars itself, perhaps from a gigantic impact early in Mars's history that blasted debris into orbit, similar to how Earth's own moon formed from a collision. In that scenario, Phobos and Deimos coalesced from a ring of rubble around Mars. Yet their low densities and cracked, battered appearances suggest they are piles of rubble rather than solid chunks of Mars. It's possible an ancient impact created a bigger moon that later broke up, producing a temporary ring and these two leftovers. The truth is, we still do not know for certain the story of Phobos and Deimos, and they remain two of the solar system's quiet enigmas. What is certain is that Phobos and Deimos are on borrowed time. Phobos orbits extremely close to Mars, so close that it actually circles the planet faster than Mars rotates. To an observer on the Martian surface, Phobos would rise in the west and set in the east, streaking across the sky in just a few hours. This proximity comes at a cost. Mars's gravity is tugging on Phobos and gradually pulling it inward. The moon's orbit is decaying a little each century. Someday, tens of millions of years from now, Phobos will spiral too close and tidal forces will tear it apart. It could break into fragments and form a thin ring around Mars for a time, or plummet piece by piece to the Martian surface. The grooves we see on Phobos's surface might even be early signs of this structural stress, subtle scratches that hint at the moon's eventual fate. Deimos, on the other hand, is slowly creeping outward, away from Mars. It may eventually escape Mars's grasp far in the future, drifting off into space. For now, though, both moons continue their ceaseless rounds, casting faint shadows on the rust-coloured ground below when the sun lines up just right. Despite their doom in the distant future, Phobos and Deimos bring a sense of motion and mystery to the Martian skies. Phobos, especially, with its rapid transit, would be a striking sight from the surface of Mars, appearing as a swift, dark dot against the twilight, sometimes crossing the sun in a brief eclipse. Deimos, smaller and farther, looks more like a bright star gliding lazily overhead. In the stillness of Mars's thin air, these two tiny moons quietly orbit, reminders of the dynamic processes that shape moons and planets. Whether born of primordial chaos or captured by chance, they are living a slow tale of orbital decay and survival. In their silence, Phobos and Deimos speak to the fragility of moons and the relentless pull of gravity. One day, Mars will lose one or both of these little attendants, but for now they remain, two small keepers of Mars's secrets, forever circling and watching over the red deserts below. Beyond Mars, a vast ring of scattered rocks and mini-worlds circles the Sun. This is the asteroid belt, a broad expanse between Mars and Jupiter, where countless fragments of the early solar system reside. Unlike the crowded scenes of fiction, the belt is mostly empty space, with its rocky members often separated by huge distances. Yet, taken together, these bodies form a kind of family that never coalesced into a single planet. They remain as diverse remnants of planetary building blocks, each with its own story, etched in stone and metal. Among the asteroids are some that resemble loose piles of rubble, barely held together by gravity. These are the shattered survivors of countless collisions. When spacecraft visited small asteroids like Itokawa and Bennu in recent years, they revealed landscapes of jumbled boulders and drifting gravel rather than solid rock. It's thought that many asteroids, especially the smaller ones, are rubble piles, reassembled clumps of debris from ancient impacts. If you were to step hard on such an asteroid, you might send a shower of pebbles floating off into space. They are worlds in the loosest sense, more a fragile congregation of fragments than a cohesive sphere. Their existence speaks of a violent past. These asteroids have been broken and reformed time and again. In contrast, some asteroids have very different hearts. A few appear to be made mostly of metal, iron, and nickel, suggesting they are pieces of the core of a long-destroyed protoplanet. One such object, 16 Psyche, lies in the middle of the belt and gleams faintly with a metallic luster. Psyche is about 200 kilometers wide and is thought to be the exposed core of an early planet that had its outer layers stripped away by titanic impacts. In essence, it's a bare metal heart, a fragment of a planet that never fully formed. Not all asteroids fit neatly into the rubble or metal categories. Consider Vesta, the second largest asteroid. Unlike most of its kin, Vesta is differentiated. It has a crust, mantle, and core, much like a tiny terrestrial planet. Its surface is coated in basalt from ancient lava flows, and a gigantic impact crater near its south pole has exposed brighter mantle rocks beneath the darker crust. Vesta was well on its way to becoming a protoplanet. In fact, meteorites that have fallen to Earth have been traced back to Vesta's crust, allowing us to study this little world's composition in our laboratories. When the Dawn spacecraft visited Vesta in 2011, it found a towering central mountain in that South Pole crater, one of the tallest known in the solar system, and confirmed Vesta's status as a fossil planet, one that started to form but was arrested by the turmoil of the early solar system. And then there is Ceres, the dwarf planet king of the asteroid belt. Ceres is by far the largest body here, a globe about 940 kilometers in diameter, massive enough that its gravity has shaped it into a round world. For 2 centuries it was just a faint point of light in telescopes, but in 2015 NASA's Dawn spacecraft arrived and unveiled Ceres' secrets. To scientists' surprise, Ceres is not merely a dormant rock, it shows signs of geologic activity. Most striking are the bright spots. Within a crater named Ocata, Dawn photographed brilliant white patches shining against the grey surface. These patches turned out to be salts, the residue of briny water that erupted from Ceres' interior and evaporated. In essence, Ceres had cryovolcanoes, cold volcanoes that oozed salty water instead of lava. One such cryovolcano, a mountain called Ahuna Mons, stands in lonely splendor on Ceres' surface, a dome of ice and salt that likely formed in the recent geological past. The salted lights of Ocata crater, as some have called them, gleam almost like beacons when viewed from space, reflecting sunlight intensely. They are evidence that Ceres, though small, retained enough internal heat, or perhaps some antifreeze chemicals in its brine, to maintain pockets of liquid that occasionally burst out. This discovery transformed our view of the belt's largest member. Ceres is a relic ocean world, hanging onto a fraction of its ancient sea deep below ground, and sometimes sending up signals of its hidden liquid heart. The asteroid belt is a miniature solar system museum. It holds fragments from nearly every stage of planetary evolution. Primitive rubble that never changed, pieces of smashed protoplanets, and even a dwarf planet bearing clues of an ancient ocean. Jupiter's gravity prevented these pieces from gathering into one world long ago, so they orbit the Sun as separate stories. Each asteroid, whether a tumbling heap of stones, a metal core glinting in sunlight, a differentiated mini-planet like Vesta, or a dwarf planet shining with salt, adds to the history of the solar system. In the quiet dark between Mars and Jupiter, this uneven family of worlds drifts on, offering clues to how planets form and how they fail. And as we leave the inner solar system, crossing the threshold of the asteroid belt, we carry with us the lessons these small worlds teach. Beyond the asteroid belt, the giants of the outer solar system wait in the cold distance. Even in emptiness between orbits, there are wonders. A dwarf planet that gleamed with salt, a metal heart of a lost world, and countless rubble siblings all circle in darkness, keeping the memory of the solar system's youth alive. A silent giant looms ahead in the darkness of space. Jupiter, king of the planets, swirls with majestic clouds of orange and white. Beneath those banded clouds and fierce storms lies an enigma. We cannot see it with our eyes, but we feel its presence through subtle gravitational whispers. Deep in Jupiter's heart, far below the swirling cloud tops, something immense and mysterious is hidden from view. If we could descend through Jupiter's atmosphere, we would enter a world of crushing pressure and dimming light. The familiar clouds would fade as we plunged deeper, replaced by darkness and intense heat. The gas around us would grow denser, the hydrogen and helium that Jupiter is made of pressing closer together. Eventually, the air would become a hot, dense fluid. At extreme depths, the pressure is so high that hydrogen, normally a gas, is squeezed into an exotic liquid metal. In this realm, electrons roam free among the tightly packed atoms, and hydrogen behaves like a flowing reflective metal. A vast global ocean of liquid metallic hydrogen lies hidden inside Jupiter, encircling its core like a secret sea. Within this metallic ocean, Jupiter generates a mighty magnetic field. As the planet rotates, the conductive fluid churns and creates a magnetic dynamo. Jupiter's magnetic field is immense and powerful, a force born from the unseen motions deep within. It's a hint of the activity and energy far below the visible clouds. The temperatures here soar to tens of thousands of degrees, and the pressures are millions of times the atmospheric pressure at Earth's surface. It is an environment utterly unlike anything on our home planet, a place where simple gas is transformed into a strange metallic form under crushing weight. At the very center of Jupiter, we expect there to be a core of heavier elements, perhaps a mixture of rock, metal, and ice that once served as the seed for this giant planet. But Jupiter guards its deepest secret well. Data from the Juno spacecraft have given us surprising clues. Instead of a compact, dense core, Jupiter's center might be fuzzy or diluted. Heavy elements seem to be spread out across a huge region, nearly half the width of the planet. There may not be a sharp boundary at all between core and mantle, as we would find in a rocky planet. Instead, Jupiter's heart could be a gradual blending, a diffuse, extended core merging into the overlying metallic hydrogen layer without a clear border. How could Jupiter's core be so diffuse? One tantalizing idea is that something catastrophic happened in Jupiter's youth. Scientists speculate that early in the planet's history, while Jupiter was still forming, it may have been struck head-on by a large protoplanet. Imagine a primordial world, perhaps 10 times the mass of Earth, plummeting into the young Jupiter. The colossal collision would have shattered Jupiter's original solid core and stirred heavy elements into the surrounding layers. The result would be a mixed-up interior, a heart scrambled and spread out by a titanic impact. Even now, billions of years later, Jupiter's diffuse core may be a scar from that ancient cataclysm, a lasting testament to the violence of its formation. It is a profound realization that Jupiter, so massive and seemingly indestructible, might have endured such a cosmic upheaval. Yet from that chaos emerged the planet we see now, still holding on to the secrets of its formation deep inside. The notion of a fuzzy core challenges our intuition. We imagine a planet as large as Jupiter must have something solid at the middle. But instead, it's as if Jupiter has a vast central region that gradually transitions from gas to a heavier mix, with no clear demarcation. It's a reminder that the gas giant is fundamentally different from the rocky worlds we know. Jupiter is less a planet with a surface, and more a gigantic sphere of fluid layers, all the way down to its mysterious heart. Though we cannot visit these depths, we can infer their nature by reading Jupiter's gravity and magnetic fields. Every pass of a spacecraft like Juno, every subtle wobble in its orbit, tells us a bit more about how mass is distributed inside Jupiter. Bit by bit, we build a picture of the hidden interior. We imagine descending through the darkness, feeling the air turn to liquid, then to metal, sensing heat and pressure beyond comprehension. We imagine approaching a core that might not be a hard sphere, but rather a vast expanse of mixed materials, gradually thickening toward the center. In that lightless central realm, the weight of all Jupiter above presses down. Time might pass differently for our imagination as we linger in Jupiter's hidden heart. It's silent and static to human senses, yet dynamic on geological timescales. Convection currents may slowly churn, moving material and transporting heat outward. Jupiter still radiates more heat than it receives from the sun, a glow from its interior left over from formation and compression. This internal heat drives much of Jupiter's weather above, powering the belts and storms we can see. In a way, Jupiter's gentle glow from within is the heartbeat of the giant planet, a reminder of the heat trapped in its core and the slow release of energy over eons. What exactly lies at Jupiter's very center remains one of the solar system's great enigmas. Is there a compact kernel of metals and rock at the core, or has it been entirely diluted into an extended cloud of heavy elements? We hope to find out more as future missions probe Jupiter's gravity and as scientists refine their models. For now, Jupiter keeps its secret deep below the clouds in crushing darkness. It's humbling to realize that the largest planet's grandest mystery is hidden where we may never directly observe it. While the core of Jupiter remains out of reach, it profoundly shapes the planet we do see. It shapes the magnetic field that sweeps millions of kilometers into space. It shapes the heat flow that stirs the atmosphere. Jupiter's hidden heart is the foundation of the giant world's present form. And though unseen, it invites us to wonder. In the darkness at Jupiter's center, we imagine a dense, alien environment, a place of extreme physics, forged by gravity and time. It is a realm where simple elements become exotic, and where the history of the solar system might be encoded in the distribution of Jupiter's inner layers. Emerging again at Jupiter's outer layers, we find ourselves among roiling clouds once more. The mysteries of the deep interior gradually give way to the mysteries of the atmosphere. Jupiter's face is marbled with patterns of light and dark, and dominating these patterns is an immense, swirling feature that has captivated humans for generations. We leave Jupiter's core behind, turning our attention now to the colossal storm that rages in the planet's upper skies, a storm that is nearly as great a mystery as the core itself. For centuries, a single storm has been raging on Jupiter, visible even through small telescopes from Earth. This is the Great Red Spot, an enormous oval of rose and copper hues set amid Jupiter's pale clouds. It rotates slowly, like a huge whirlpool, an anticyclone larger than our entire planet. Through the eyepiece of a telescope, it appears as a distinct red blemish on Jupiter's banded disk. Up close, as spacecraft have shown us, the spot is a swirling maelstrom of clouds, with concentric layers and turbulent eddies at its edges. The Great Red Spot resides in Jupiter's southern hemisphere, about 22 degrees south of the equator. It rotates counterclockwise, completing a rotation roughly every 6 Earth days. Within this gargantuan storm, winds rage around its periphery at hundreds of kilometers per hour. By contrast, the center of the storm is relatively calm, a high-pressure region with gas slowly sinking. The spot's oval shape is bounded by jet streams, powerful east-west winds above and below that corral the storm, keeping it in place. Without a solid surface to disrupt it, this vortex can persist far longer than any terrestrial hurricane. No one alive today was born before the Great Red Spot existed. It has been continuously observed for well over 150 years, and likely much longer. Early astronomers in the 1600s may have glimpsed a spot on Jupiter that could have been this storm or its ancestor. By the 19th century, it was regularly noted and sketched, already a prominent feature of Jupiter's face. In those times, it appeared larger and very distinct. Over the decades, humanity has watched the Great Red Spot with fascination, aware that we are witnessing a storm that predates modern science itself. It is humbling to think that when Galileo first pointed his telescope at Jupiter in 1610, the storm might have already been churning for unknown years, and it continues to this day. The storm's longevity is one of its greatest mysteries. On Earth, even the mightiest hurricanes last only a few weeks before dissipating. But Jupiter's Great Red Spot has endured for centuries. Part of the reason is Jupiter's composition. It is a planet of gas, lacking continents or oceans to weaken a storm. The red spot simply swirls over Jupiter's deep atmosphere, unimpeded by land. Additionally, Jupiter's internal heat supplies energy from below. Jupiter radiates more heat than it gets from the Sun, and this energy likely helps sustain large weather systems. The Great Red Spot may be continually fed by surrounding jet streams and smaller storms, which merge into it and reinforce its rotation. In Jupiter's vast atmospheric engine, the red spot has found a stable niche, spinning like a gigantic flywheel that just keeps going. Though persistent, the Great Red Spot is not unchanging. Over the past century, astronomers have observed it slowly shrinking. Old observations from the late 1800s suggest the spot once stretched over 40,000 kilometers in length, wide enough to fit 3 Earths side by side. In the 1970s, when the Voyager probes flew by Jupiter, the storm was roughly 23,000 kilometers across. By the 21st century, it had contracted to about 16,000 kilometers across, only a bit larger than Earth's diameter. Today, it continues to reduce in size, appearing more circular than oval. At around 10,000 to 15,000 kilometers across now, it could fit just a little over 1 Earth within it. This gradual shrinking has been carefully documented by telescope images year after year. Scientists project that if the trend continues, the Great Red Spot might become truly circular by a few decades from now, and perhaps eventually diminish further. Yet, despite getting smaller, it remains a colossal storm by any measure, still the largest known storm in the solar system. As it shrinks, the storm has also fluctuated in color and intensity. Sometimes the red spot appears a vivid brick red. Other times it fades to a pale salmon or even whitish hue. The causes of these color changes are still debated. The red color may come from complex organic molecules or sulfur compounds, dredged up from deeper layers and altered by sunlight. It could be chemicals like phosphorus or nitrogen compounds, tinted red under ultraviolet light. We know the clouds in the red spot are higher and colder than most surrounding clouds, and different chemistry might be at play within the vortex. When the color fades, it might indicate changes in the composition or altitude of those clouds. Then, suddenly the spot can deepen in redness again as new material is pulled up from below. The shifting tones of the great red spot add to its aura of mystery. It's as if the storm breathes, blushing and paling over the years. Recent observations have revealed dramatic events at the red spot's edges. On a few occasions, small eddies and streamers have been seen peeling away from the main oval, a phenomenon some dubbed flaking. These fragments of red would spin off and dissipate, leading to speculation that the Great Red Spot could be destabilizing. Around 2019, a series of such events was observed, causing excitement and concern that the long-lived storm might finally be breaking apart. However, the core of the red spot persisted, and many scientists now think that these apparent peelings were interactions with other nearby storms or turbulence, not signs of the spot's imminent demise. The Great Red Spot has survived countless encounters. Smaller storms have bumped into it, even been absorbed by it, and yet it endures. It's likely that the flaking episodes were superficial, involving its cloud layers, but not destroying the deep vortex underneath. Deep inside the Great Red Spot, there is more than meets the eye. NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, carried instruments to probe beneath Jupiter's cloud tops. When Juno flew over the red spot, it used microwave sensors and gravity measurements to gauge how far down the storm extends. The findings were astonishing. The Great Red Spot reaches at least 300 kilometers, about 200 miles, into Jupiter's atmosphere, maybe even deeper. In terms of pressure, the storm's base plunges to levels well over 100 times the pressure at Earth's sea level, far below the visible cloud deck. This means the red spot is not just a surface feature. It is a deep, well-rooted system that extends through multiple layers of Jupiter's sky. The data also showed that at those great depths, the storm is warmer at the bottom than at the top. Warmer base temperatures could provide the energy to keep the storm going, with heat driving upward and powering the circulation. Another intriguing discovery is that the Great Red Spot seems to heat the upper atmosphere high above Jupiter. Hundreds of kilometers above the storm, the air is surprisingly warmer than in other regions at that altitude. One theory is that the turbulence of the red spot produces acoustic or gravity waves that travel upward. When these waves break in the thin upper atmosphere, they release their energy as heat. In essence, the storm's fury reverberates upward and warms the high atmosphere above it. This creates a local hotspot high over the Great Red Spot, meaning this one storm's influence extends from deep below the clouds all the way to the fringes of space around Jupiter. Standing on the cloud tops near the Great Red Spot, if one could ever do so, would be an awe-inspiring experience. You would see a towering wall of clouds curving around a vast ochre oval, swirling and twisting. Winds would be howling at the periphery, but deep inside the oval there might be an uncanny calm, the eye of a centuries-old storm. Lightning might flash in the surrounding belts, but within the red spot, conditions could be more stable, dominated by the slow, massive churn of the vortex. It is a cyclone of a scale beyond anything on Earth, a weather system that could engulf entire planets. Yet for all we have learned, we still do not know how long the Great Red Spot will last. Is it a permanent feature of Jupiter that only occasionally waxes and wanes? Or is it a transient megastorm in its final centuries of life? Some models suggest the red spot could dissipate within a human lifetime if its shrinking continues unabated. Others argue that the storm could stabilize and persist for much longer, perhaps waxing and waning in cycles that we have yet to understand. The truth is, we have never witnessed something like this from beginning to end. Our observations cover only a few hundred years of what could be a much longer story. For now, the Great Red Spot still holds court on Jupiter, changing subtly but refusing to die. Every time we aim our telescopes at Jupiter, we check on this ancient tempest. And every time, it's there. Sometimes a bit smaller, sometimes a bit lighter or darker, but still spinning, century after century. The Great Red Spot has become an icon of Jupiter's dynamic atmosphere, a symbol of persistence amid change. As we leave Jupiter behind, we venture outward to the next giant planet. Saturn appears ahead, adorned with its magnificent rings. Even from a distance, Saturn's rings gleam like a cosmic jewel, a broad flat disk encircling the pale gold planet. For generations they have captivated our eyes and our imagination. Now, as we approach, the true complexity of the rings begins to reveal itself, and with it, new puzzles about their origin and fate. Saturn greets us with its breathtaking rings on full display, a celestial marvel of the outer solar system. The planet itself is a pale golden globe banded with subtle clouds, but it is the rings, broad, flat, and shining, that capture our imagination. They encircle Saturn like a giant disk of light, thousands of kilometers wide, but just a few tens of meters thick in most places. From afar, the rings look solid and serene, a continuous hoop of material. As we draw closer, however, we see that they are made of countless individual pieces, chunks of ice and rock ranging from dust grains to boulders, all orbiting Saturn in a thin plane. The rings glint in the sunlight, a cosmic dance of ice particles that has enchanted sky gazers for centuries. For a long time, scientists assumed Saturn's rings were ancient, perhaps as old as the planet itself. Saturn formed over 4.5 billion years ago, and one idea was that the rings are leftover debris from that era, a remnant of the disk of gas and dust that coalesced to form the planet. However, evidence gathered in recent years has challenged this assumption. Saturn's rings might be far younger than we imagined. Data from the Cassini spacecraft, which orbited Saturn in the 2000s and 2010s, suggests the rings formed only tens of millions of years ago, potentially during the age of the dinosaurs on Earth. Such a recent origin, in geological terms, is a startling revelation. For most of Saturn's existence, it might have been a planet without the majestic rings we see today. What led scientists to conclude the rings are young? A few key clues come from the rings' composition and apparent purity. Saturn's rings are made mostly of water ice, which appears bright and reflective like freshly fallen snow. Over billions of years, one would expect the rings to accumulate dark dust and micrometeorite debris, which would dirty the ice and dim their luster. Yet Saturn's rings are remarkably bright and clean, more like fresh snow than ancient, soot-stained ice. This suggests they haven't been exposed to cosmic pollution for billions of years, but perhaps only for a shorter time. Another clue came during Cassini's final mission phase, when the spacecraft dove close to the rings and measured their mass. The rings turned out to have less mass than many had assumed for an ancient system. A lower mass, coupled with their brightness, implies the rings could not have survived intact for billions of years without becoming dark and depleted. Combining these observations, Researchers estimate the rings likely formed somewhere between 10 and 100 million years ago, a relatively recent addition to Saturn's family. If Saturn's rings are indeed young, how did they form? One prevailing theory is that they are the remnants of a shattered moon or a wayward comet that got too close to Saturn. Perhaps a large icy moon strayed within Saturn's Roche limit, the region where the planet's tidal gravity can tear an object apart, and was ripped to pieces. The debris would have spread out around Saturn, forming a ring. Over time, the countless fragments flattened into the thin, delicate rings we see today. Another possibility is that a comet or a group of comets were captured and disintegrated. In either case, the rings could be the aftermath of a cosmic breakup that happened long after Saturn formed. It's a dramatic origin story. The grand rings might be the graveyard of an object that disintegrated in Saturn's grip, turning destruction into something of transcendent beauty. What is the future of Saturn's rings? The evidence suggests that they may be transient on cosmic timescales. Even now, the rings are slowly losing material. A phenomenon known as ring rain is drawing ring particles down into Saturn's atmosphere. Saturn's gravity, along with its magnetic field, causes a steady drizzle of fine, charged ice particles to spiral inward from the rings and fall into the planet. Cassini confirmed that the rings are shedding matter continually. A steady rain of material falls into Saturn. Observations indicate that this rain is surprisingly heavy. If ring rain continues unabated, the rings could largely vanish in as little as 100 million years. A fleeting moment on cosmic scales. Saturn likely spent most of its past without rings, and it may lose them again in the future. We are fortunate to observe the planet during the relatively brief epoch of its magnificent rings. Such a time span is extremely short compared to Saturn's total lifetime. Meanwhile, as the rings gradually wane, they are not static. They interact with Saturn's environment and its moons in complex ways. Saturn's moons can contribute material to the rings or steal from them. Micrometeoroid impacts on moons can kick up dust that ends up in the rings. In turn, ring particles that drift inward eventually burn up in Saturn's atmosphere, and some particles can be gravitationally captured by moons. Cassini discovered that the rings are even dumping complex organic molecules into Saturn's upper atmosphere, along with water. A surprising find that shows the ring rain isn't just pure ice. The rings, in effect, act as a conduit, delivering material to Saturn and perhaps swapping ingredients with the moons. Small moons, called shepherd moons, play a crucial role in maintaining the ring's sharp structure. These tiny moons, often only a few tens of kilometers across, orbit within or just beyond the rings. Their gravity herds the ring particles, confining them to narrow bands or sharp edges. For example, the moons Prometheus and Pandora flank the narrow F ring and effectively keep it together, reining in stray particles. Tiny Pan and Daphnis orbit within gaps in the rings, the Encke gap and Keeler gap, respectively, sweeping those gaps clean and corralling the ring particles around them. The influence of these moonlets prevents the rings from dispersing too quickly and creates some of the patterns we see. Like cosmic shepherds, they use gravity to guide the flock of particles, sculpting the rings into distinct lanes and fringes. The story of Saturn's rings is one of constant change. Born from a cataclysm not so long ago, dazzling in the present, and destined to dissipate in the future. The rings connect to the planet and moons in a complex dance of gravity and material exchange. They also connect to our sense of wonder, reminding us that even monumental structures in our solar system have life cycles. As we take in the splendor of Saturn's rings in this moment, we also sense their fragility and impermanence. The very processes that likely created the rings now slowly unmake them. Within the expanse of Saturn's rings lies a world of fine details. The broad bands that appear uniform from Earth resolve into countless ringlets, gaps, and ripples upon closer look. These intricate structures are a record of subtle gravitational forces at work. Having considered the age and fate of the rings, we now delve deeper into their patterns. Up close, Saturn's rings reveal braids, divisions, and waves, all sculpted by the gravitational tugs of moons and resonances, the unseen sculptors behind the ring's elegant structure. From up close, Saturn's rings are anything but uniform. Instead of a single flat sheet of particles, they are a tapestry woven with gaps, waves, and braided strands. Fine details ripple through the rings, patterns that tell of invisible influences. The more we look, the more structure we see. Narrow divisions cutting across the rings, edges that undulate, and ringlets that bunch together or spread apart. These features are the handiwork of gravity, sculpted by Saturn's moons and by resonances that send subtle shivers through the swarm of orbiting ice. One of the most prominent features in Saturn's rings is the Cassini division, a wide dark gap that separates the bright A and B rings. To the eye, it looks like an empty band. This gap did not form at random. It is carved by a gravitational resonance with Saturn's moon Mimas. Mimas orbits outside the rings and circles Saturn in such a way that its gravity repeatedly tugs on particles that would orbit within the Cassini division. Each time ring particles come to a certain point in their orbit, Mimas's gravity gives them a nudge. Over time, these regular tugs clear out that region, leaving a broad gap. In essence, the rhythm of the moon's orbit sweeps the gap clean, confining ring particles to either side. Not all gaps in the rings are caused by distant resonances. Some are directly occupied by small moons that act as ring sculptors. The Encke gap, a narrow opening in the outer A ring, is home to a little moon named Pan. Pan's gravity gathers up ring particles along its path, effectively sweeping its orbit clear and maintaining the gap. As Pan travels through the ring plane, it also produces waves along the gap's edges, scalloping patterns where particles bunch up from Pan's periodic pull. Similarly, another moonlet, Daphnis, inhabits the Keeler gap at the outer edge of the A ring. When Cassini photographed Daphnis up close, we saw waves not only in the ring plane, but rising above and below it, like ripples or corrugations in the ring material. Daphnis, only about 8 kilometers across, manages to draw ring particles into a neat wave pattern through its gravity as it passes. These moonlets act like boats in a crowded pond, their wakes leaving lasting impressions in the sea of particles. Perhaps the most visually intriguing of the ring structures is the F ring, a narrow, thread-like ring just outside the main ring system. The F ring has been observed to appear braided and kinked, as if several strands of ring material were entwined. This strange braid is caused by the interplay of two shepherd moons, Prometheus and Pandora, that orbit on either side of the F ring. Prometheus periodically dips just inside the ring, stealing some material and pulling streams of particles along with it, which creates a series of knots or clumps in the ring. Pandora, on the outside, helps keep the ring confined to a tight band. The combined pull of these moons causes the F ring's core to wobble and its particles to bunch up. Parts of the F ring look woven together, then drift apart. It's a constantly evolving structure, its pattern rewoven with each pass of its shepherding moons. Beyond the obvious gaps and braids, Saturn's rings also contain more subtle patterns. waves that spiral through the ring material. Some of these are density waves, essentially waves of compression, triggered by resonances with more distant moons. For example, a moon might tug on ring particles at just the right interval to send a ripple propagating through the ring, like a wave spreading out in water. These waves appear as alternating dense and sparse regions in the rings, often in graceful spiral patterns. Cassini's instruments detected dozens of such density waves, each corresponding to a specific moon's influence. They are tightly wound spiral ripples, a record of a whisper from a moon, imprinted on the collective behavior of billions of ring particles. There are also vertical waves that tilt ring particles out of the flat plane, caused by moons whose orbits are slightly inclined relative to the rings. These vertical perturbations create a slight waviness in the ring plane, like a ripple that goes up and down. One famous example is a warp in Saturn's D ring, the innermost faint ring, thought to be caused by a past collision or by Saturn's tilted gravitational field. This warp forms undulations that Cassini observed as the rings alternately rose and fell by a few tens of meters. Not all shapers of the rings are directly seen. Cassini discovered peculiar disturbances in the rings called propellers, small S-shaped patterns in certain ring bands. These propellers are caused by moonlets too small to be observed directly, perhaps only a few hundred meters across. The gravity of such a hidden mini-moonlet slightly pushes ring particles aside along its orbit, creating a pair of opposing wakes that resemble the twin blades of a propeller. These structures drift through the rings, revealing the presence of many tiny, unseen moons. In a sense, the rings allow us to detect invisible objects by their influence, just as we infer unseen planets around distant stars by their gravitational tug on starlight. The propeller patterns show that Saturn's ring system is not just a static collection of debris, but a dynamic disk with ongoing interactions at all scales. All these patterns, the cleared gaps, the rippling waves, the braided strands, show us that Saturn's rings are orchestrated by gravity's subtle hand. The particles in the rings are continually nudged and herded by Saturn's entourage of moons. In some regions, the rhythm of a moon's orbit establishes order, as in the Cassini division. In others, an embedded moon sculpts a sharp edge or gap. Even far-off moons whisper to the rings through resonances, creating spiral harmonies in the particle ensemble. The result is an ever-changing but beautifully structured disk, a cosmic record groove encoding the gravitational music of Saturn and its moons. Watching the rings in motion, one can sense that this is a living system, dynamically responding to influences around it. The changes occur slowly by human standards, waves taking years to travel, ringlets shifting over decades. But they are happening. Saturn's rings are not a frozen picture, but a symphony in slow time. If we could watch a sped-up movie of the rings over millennia, we would see waves oscillate, ring edges bend in and out, and gaps widen or narrow as moons migrate, or as resonances shift. It's a reminder that even something as seemingly permanent as Saturn's rings is full of activity and change. Our journey through the realm of the giants has shown us colossal planets and dynamic rings. But the giant planets also share their realm with an array of moons, some of which harbour secrets as compelling as the planets themselves. Not all mysteries of the outer solar system swirl in atmospheres or dance in rings. Some lie hidden beneath surfaces of ice. Gravitational forces that sculpt rings can also heat the interiors of moons, creating warm havens in the cold. We venture now to explore the unseen oceans beneath the icy crusts of distant moons, places where water flows in permanent night, warmed by the gentle kneading of gravity. Far from the sun's warming rays, in the cold outer reaches of the solar system, one would expect only frozen worlds. Indeed, the surfaces of many moons of Jupiter and Saturn are ice-cold and solid. Yet, hidden beneath some of those icy crusts are liquid water oceans, environments that seem astonishing in such a frigid domain. These secret seas are kept liquid not by sunlight, but by the internal heat generated through gravitational tug-of-war. As giant planets flex and squeeze their moons, the energy of that tidal kneading warms their interiors. The result is one of the most surprising discoveries in planetary science. Oceans beneath ice, warm havens of water encased in shells of perpetual frost. Jupiter's moon Europa is a prime example of this phenomenon. Europa is about the size of Earth's moon and is coated in a shell of water ice, perhaps 15 to 25 kilometers thick. Its surface is a bright, smooth expanse, crisscrossed by long, dark lines, cracks and ridges that streak across the moon. These lines hint at a restless interior. Unlike heavily cratered moons, Europa's surface looks relatively young, with few large craters, suggesting that some process has been resurfacing it over time. Beneath Europa's frozen exterior lies a global ocean of liquid water. Scientists estimate this subsurface ocean might be on the order of 100 kilometers deep, meaning that Europa could harbor more water in its hidden sea than all of Earth's oceans combined. How do we know Europa has an ocean we cannot see? The evidence comes from multiple sources. NASA's Galileo spacecraft, which orbited Jupiter in the 1990s, measured Europa's magnetic environment and found perturbations consistent with a conductor beneath the ice, likely a salty liquid ocean interacting with Jupiter's magnetic field. Additionally, the patterns of Europa's surface cracks and ridges suggest the ice shell is moving or floating on something fluid below, with tides causing the crust to flex and fracture. Images show regions of chaos terrain, where great blocks of ice appear to have broken apart and drifted, as if ice rafts were bobbing on a liquid below. This may indicate warm water, or slush, upwelling from the ocean and partially melting the crust. In recent years, the Hubble Space Telescope has reported faint signs of water vapor above Europa's surface, hinting at occasional plumes of water erupting through the ice. Indeed, a reanalysis of older spacecraft data also found tantalizing evidence for such plumes. If these geysers are confirmed, they would offer direct proof of Europa's ocean communicating with the surface. Scientists are excited by this possibility because it means a future spacecraft could potentially sample the ocean's contents simply by flying through the plume, a way to taste the hidden sea without drilling through the ice. Europa's ocean exists because of a process known as tidal heating. As Europa orbits Jupiter, it experiences varying gravitational pulls. Its orbit is slightly elliptical, and resonances with its neighbouring moons, Io and Ganymede, ensure that Europa is alternately closer to and farther from Jupiter over the course of an orbit. The result is that Europa is constantly flexing. Imagine a rubber ball being squeezed rhythmically. This flexing generates internal friction and heat within Europa's interior. Without Jupiter's pull, Europa would be an ice-solid sphere. With it, Europa's interior stays warm enough to keep a deep ocean liquid. Thus, even at over 5 AU from the Sun, where sunlight is weak, Europa maintains a vast ocean beneath its ice, heated by gravitational energy. The idea of a warm ocean sealed below an icy crust is as intriguing as it is mysterious. In that dark ocean, there is no sunlight, but there could be other sources of energy, perhaps hydrothermal vents on the ocean floor, where mineral-laden hot water pours out of rock, as happens in Earth's deep oceans. On Earth, such vents teem with life despite the darkness, drawing energy from chemistry instead of the sun. We don't know if anything swims in Europa's hidden sea, but the basic ingredients for life as we know it, liquid water, heat energy, and chemistry, appear to be present. Europa has become a tantalizing target in the search for extraterrestrial life, precisely because of this hidden ocean. The notion that an entire ocean, potentially containing more water than Earth's, has persisted beneath Europa's ice for billions of years, raises profound questions. Could life have arisen there? What kind of strange organisms might dwell in an alien sea that never sees the sun? Moving farther out in the solar system, we find another remarkable ocean-bearing world, Saturn's small moon, Enceladus. Enceladus is about 500 kilometers across, small even compared to Europa, and is coated in bright, clean ice. For ages, Enceladus appeared unremarkable apart from its bright ice. That changed in 2005 when the Cassini spacecraft, while exploring Saturn, noticed something extraordinary at Enceladus. Plumes of water vapor and fine ice were erupting from its south pole. Geysers were spraying out through long fractures in the ice, later nicknamed tiger stripes, forming giant fountains that extended hundreds of kilometers into space. These geysers immediately signaled that Enceladus had liquid water beneath its surface. Cassini even flew through the plumes to sample their composition. It found they were composed mostly of water vapor, with plenty of tiny ice grains, essentially a cryovolcanic spray of cold water. Mixed in were salts like sodium and potassium, and even simple organic molecules. This cocktail strongly suggested that the water in Enceladus's interior was in contact with rock, picking up salts and minerals, much like seawater on Earth. All these clues, from the salts to the organics to the tiny silica grains, indicate that Enceladus's ocean interacts with its rocky core at high temperatures, akin to hydrothermal vents on Earth. We now understand that Enceladus hosts a global ocean beneath an ice crust, perhaps 20 to 30 kilometers thick, at least in the South Polar region. The ice may be thicker elsewhere. The ocean lies between the ice shell and a rocky core. Saturn's gravitational pull, along with tugs from neighboring moons, flexes Enceladus and provides heat, much as Jupiter does for Europa, though on a smaller scale. That heat keeps Enceladus's interior ocean liquid. The cracks at the South Pole, those tiger stripes, act as vents where the pressurized water can escape as jets. Each eruption spews tons of water and ice particles into space. In fact, the continuous spray from Enceladus's geysers replenishes Saturn's faint E-ring with fresh material. This tiny moon, through its geysers, manages to influence the entire Saturnian system. The discovery of Enceladus's plumes has profound implications. It means we can sample an alien ocean without drilling. The moon is effectively spraying its ocean into space for us. Cassini's taste of Enceladus's plume revealed water, organics, and signs of hot water chemistry. These are ingredients associated with habitability. Enceladus has therefore become, like Europa, a prime target in the search for possible life. If microbes exist in its dark sea, perhaps traces of their presence, complex organic compounds or other signatures, could be lurking in the plume particles. Future missions might fly through those plumes with even more sensitive instruments, seeking hints of biology in the ejected ice. What is truly wondrous is how nature has created warm, wet havens in the least likely places. Enceladus orbits Saturn, at a distance where sunlight is feeble and surface temperatures are extremely low, around 200 degrees C on the ice. Europa, though closer to the Sun than Saturn is still a frigid world where water is rock hard at the surface. Yet both moons conceal oceans as dynamic and wet as Earth's beneath their frozen exteriors. It is the gravity of their giant parent planets that provides the energy, an internal furnace stoked by the push and pull of orbits. Warmth in the cold, darkness below, but possibly life-sustaining conditions. As we contemplate these alien oceans, we are reminded of how special and diverse the solar system is. Liquid water, which we often think of as requiring Earth-like warmth, turns out to exist in unlikely corners when the conditions are right. Worlds once assumed to be inert ice balls can hide warm oceans and perhaps even life's potential. No longer do we look only at planets in the habitable zone. We also look to icy moons around giant planets, where tidal forces create habitable niches in the darkness. Having glimpsed these warm, hidden oceans, we now turn to a very different kind of sea. In the next stage of our journey, we set course for Titan, Saturn's largest moon, where an exotic cycle of methane rain and lakes offers a mirror to Earth's water cycle, played out in a world of perpetual twilight. We arrive at Titan, Saturn's largest moon, and immediately find ourselves in a world both hauntingly familiar and utterly alien. Titan is wrapped in a dense atmosphere that shrouds its surface in a perpetual orange haze. This thick air, mostly nitrogen with a dash of methane, is so murky that sunlight barely penetrates, casting an eternal twilight over the landscape. In this dim glow, a complex weather system unfolds. But unlike Earth's, Titan's weather is based not on water, but on methane. Here, the roles of sky, rain, and sea are all played by hydrocarbons. Titan is the only place in the solar system, aside from Earth, known to have stable liquid lakes and seas on its surface, though on Titan, the liquid is frigid methane and ethane, not water. Titan's surface, as revealed by the Cassini spacecraft and the Huygens probe that landed there, is a diverse and eerie tableau. Near Titan's equator, vast dark dunes stretch across the terrain, reminiscent of desert sand dunes on Earth. But these dunes are not made of silicate sand. They are composed of grains of complex organic material, essentially sand made of frozen hydrocarbons that fall from Titan's hazy sky. The dunes, sculpted by gentle winds in Titan's dense atmosphere, can reach hundreds of kilometers in length, forming parallel ridges around the moon's midsection. They speak of an active surface shaped by wind over long periods. Traveling toward Titan's higher latitudes, the terrain changes. Cassini's radar instruments discovered large, smooth areas near Titan's poles that reflected signals like liquid surfaces. These turned out to be lakes and seas of methane and ethane, some of them vast. Titan's North Pole, in particular, is dotted with sizable bodies of liquid. The largest, Kraken Mare, is a methane sea that spans hundreds of kilometers, comparable in size to Earth's Great Lakes. There are also many smaller methane-filled lakes with shorelines etched into Titan's icy crust. One lake, Ligeia Mare, is rich in liquid hydrocarbons and is larger than Lake Superior. Seeing these features was astounding. We found coastlines, bays, islands, and channels on a world more than 1 billion kilometers from the Sun. Titan experiences seasons during its 29.5-year orbit around the Sun. And these seasons drive a methane cycle much like Earth's water cycle. In Titan's warmer summer hemisphere, sunlight, weak though it is, causes more methane to evaporate from the surface into the atmosphere. Titan's cold, thick air can carry this methane aloft, forming clouds. Scientists have indeed observed large methane cloud systems, especially around the times of seasonal change, and occasionally these clouds unleash methane rainstorms. When it rains on Titan, it is liquid methane that falls from the clouds, wetting the surface and darkening the ground. The Huygens probe, which parachuted through Titan's atmosphere in 2005, photographed what looked like carved river channels and drainage patterns, strong evidence that liquid flowed there, likely from a past methane rainfall. The probe's instruments also found Titan's ground to be moist where it landed, suggesting it had rained not long before its arrival. Titan's rains feed its lakes and seas. During Titan's long winter, particularly at the poles, methane accumulates on the surface in liquid form. In spring and summer, some of those polar lakes evaporate under the slight warmth of the sun, adding humidity to the atmosphere and leading to cloud formation. Cassini watched Titan over the course of years and saw changes that hint at this seasonal filling and drying. For instance, one region near the equator showed a darkening after a large cloud system dissipated, possibly a transient puddle or wet surface from recent rain. One especially intriguing observation was of a feature nicknamed the Magic Island in one of Titan's northern seas, an area that appeared bright in one radar pass, vanished in another, and then reappeared. It might have been caused by changing conditions on Titan's sea, perhaps waves picking up as winds increased, or bubbles rising from the sea floor, temporarily making the sea surface rough. The climate on Titan is, in many ways, an analogue to Earth's, but with dramatically different ingredients. Titan's average surface temperature is around 179 degrees, so water there is as solid as stone. Indeed, Titan's bedrock is water ice as hard as rock at those temperatures. Methane, which is a gas on Earth, exists as a liquid on Titan. Thus, Titan has riverbeds and lake basins, but they are carved into hard ice, and the liquid that fills them is methane. Titan has rain, but it is a drizzle of liquid natural gas. The orange smog in Titan's sky is caused by sunlight-driven chemistry. Methane and nitrogen react to form complex organics that fall like fine soot. This steady rain of particles likely supplies the material for Titan's dunes and coats the surface with a dark, organic veneer. Despite the exotic chemistry, standing on Titan's surface with the right protective gear might feel oddly familiar. The atmospheric pressure at Titan's ground is about 1.5 times the pressure at Earth's sea level, a gentle, cushiony atmosphere around you. The diffuse sunlight filtering through the orange haze would give the landscape a dim amber glow, akin to late twilight on Earth. You might see a few clouds hanging in the sky. Around you could lie pebbles and chunks of water ice, scattered like rocks. If you were near Titan's poles, you might even gaze upon a mirror-still methane lake extending to the horizon, reflecting Saturn's distant glow in a coppery sky. It is an otherworldly scene, yet shaped by processes we know: rain falling, liquid pooling, evaporation and wind, all transplanted into alien conditions. Titan's methane cycle likely has been active for millennia, but there remains a puzzle. Methane in the atmosphere is gradually destroyed by sunlight over geological timescales. If Titan has had methane for billions of years, what replenishes it? Scientists suspect there are reservoirs of methane beneath Titan's surface, maybe trapped in clathrates, ice lattices, or in subsurface pockets, that slowly release methane to keep the cycle going. It's also possible that methane is continually produced by chemical processes in Titan's crust or mantle. Some even speculate about cryovolcanoes on Titan, ice volcanoes that could erupt with methane or other liquids from the interior. So far, no clear-cut cryovolcano has been observed, but Titan's surface shows some features that might be candidate ice volcano domes. The persistence of Titan's thick atmosphere and lakes suggests a dynamic balance between methane loss and replenishment. It's one more mystery that Titan holds in its atmosphere and crust. As we wrap our journey at Titan, we see a world that, at first glance, looked like a featureless orange orb, but upon closer inspection reveals a complex, active environment. There are rains and rivers, lakes and seas, winds and dunes, a full cycle of liquids and gases at work, just with different chemistry in the deep cold. Titan offers a striking example of nature's inventiveness, a frigid moon that has an Earth-like weather and hydrological cycle, but with methane as the key ingredient instead of water. It makes us wonder if similar weather might exist on far-off exoplanets with different compositions, or what other surprises await among the lesser-known worlds of our own solar system. Our exploration of the giants and their moons has taken us through storms, rings, and hidden oceans. But even as we linger on Titan's alien shores, our journey is not yet over. Beyond the realms of Jupiter and Saturn lie the outer planets Uranus and Neptune, mysterious ice giants that hold secrets of their own, and beyond them, the distant frontier of the Sun's domain. In our next and final part, we will venture outward one more time to explore the enigmas of those farthest worlds and to reflect on the wonders we have encountered in our voyage through the solar system's enigmas. Not far beyond the warm glow of the sun, a pale blue-green planet rolls around the sky on its side. This is Uranus, uniquely tipped over more than 90 degrees from the normal upright orientation of planets. Each pole of Uranus points almost directly toward the Sun for part of its orbit, resulting in a bizarre seasonal cycle. One pole basks in continuous sunlight for 42 years, while the opposite pole endures 42 years of darkness. Then they trade places. In these prolonged summers and winters, the Sun arcs low above one horizon or hides below it for decades at a time. Such extreme seasons unfold in slow motion, making Uranus's climate unlike that of any other world. Astronomers have long wondered what cosmic event could topple an entire planet onto its side. The leading theory is that during Uranus's infancy, it was shattered by a titanic impact. In the young solar system, a protoplanet, perhaps 1 to 3 times the mass of Earth, may have barreled into Uranus and knocked it over like a spinning top. This cataclysmic collision would explain why Uranus's axis is tilted by 98 degrees and why the planet spins so rapidly, one rotation in about 17 hours. Tellingly, Uranus's 27 moons and faint rings also lie in the same skewed plane, as if frozen in place after that ancient blow. Such evidence strongly suggests Uranus still bears the scar of that long-ago disaster. If a single giant impact produced Uranus's tilt, it must have been world-altering. Yet curiously, Uranus today still retains an atmosphere and a retinue of moons that orbit calmly around its equator. Simulations of a lone massive impact have struggled to reproduce the system we see. For example, Uranus's large moons remain in regular, circular orbits, rather than being thrown into chaotic paths. To resolve this puzzle, some scientists have proposed that Uranus might have been struck twice in succession. 2 smaller impacts could potentially roll the planet on its side more gradually, without completely disrupting an early moon system. Debris from these collisions might have settled into an equatorial disk, from which Uranus's moons later coalesced. This double whammy hypothesis elegantly accounts for a tilted planet with moons still orbiting in the planet's equatorial plane. Others have speculated whether slow, steady forces could have tipped Uranus over, perhaps a long-term gravitational tug or resonance during the solar system's formation. But no gentle mechanism explains an axial tilt of 98 degrees. The evidence points to violence in Uranus's past. If we could rewind the solar system's clock, we might witness Uranus being sideswiped by a wayward world and sent tumbling. Today, Uranus quietly rolls along on its side, its poles taking turns facing the distant sun. The planet's skewed orientation stands as a lasting monument to a primordial upheaval. Down on Uranus's cloud tops, the consequences of this great tilt are profound. Each pole spends decades either bathed in sunlight or cloaked in darkness. At Uranus's north pole in midsummer, the sun would hang low in the sky and circle endlessly, never setting for years on end. Then, as the planet moves along its 84-year journey around the sun, that pole is plunged into an equally long night, a twilight lasting 4 decades, lit faintly by stars and the distant sun. These drawn-out seasons likely influence Uranus's weather. For much of the time that humans have observed Uranus, it appeared as a bland, aquamarine globe with barely any visible clouds or storms. Only around 2007, when the sun's direct rays crossed Uranus's equator during the equinox, did astronomers notice a flurry of activity. Bright methane-white clouds and a few dark spots erupted in the atmosphere, as if the sudden change in solar illumination stirred up long, sleepy weather systems. Even so, Uranus's weather has remained far more sluggish and subtle than the stormy patterns seen on other giant planets. Perhaps the planet's languid 42-year day-night cycles even out its climate, preventing extreme winds. Or perhaps the ancient impact shook Uranus's interior in ways that dampened the energy available to drive dramatic weather. The same ancient collision that knocked Uranus on its side may have left another lasting imprint, an unusually cold interior. Unlike its neighbour Neptune, which radiates a substantial amount of internal heat, Uranus appeared to emit almost no heat of its own. For decades, Uranus puzzled scientists by seeming to give off just as much energy as it received from the Sun. No more. All other giant planets release significant leftover heat from their formation. So why not Uranus? Some researchers guessed that Uranus might be an exceptionally old, cooled-off world. Others speculated that the cataclysmic impact which toppled Uranus might have somehow blown out or impeded its internal heat. Maybe the collision vented Uranus's warmth to space, or maybe it created a layered interior that trapped heat from escaping. Without better data, the missing heat of Uranus remained a persistent mystery. Recently, however, scientists have revisited old Voyager 2 data with new modelling techniques and found that Uranus isn't quite as cold inside as we thought. It does emit a little more energy than it receives, roughly 15% more, according to the latest estimate. This faint warmth was hard to discern with Voyager's single snapshot, but by accounting for Uranus's reflectivity and seasonal changes, researchers teased out a small internal heat flux. Even so, Uranus's heat output is feeble compared to Neptune's. Neptune radiates more than twice the energy it gets from sunlight, whereas Uranus's trickle of extra heat is minuscule. The contrast is striking. Neptune's internal furnace drives active belts and storms, while Uranus's meager heat leaves it with a relatively inert atmosphere. Why are two planets of similar size and composition so different in their internal heat? Part of the answer may lie in their divergent histories. Uranus's violent upheaval could have fundamentally altered its interior. Some simulation studies suggest that a giant impact might have disrupted Uranus's core and stifled its ability to transport heat. If layers of different composition formed after the impact, they might act as insulation, preventing heat from escaping. Neptune, having avoided such trauma, retained a more efficient heat transport and thus a warmer interior. Another possibility is ongoing chemical and physical processes. Deep inside these planets, unusual phenomena could generate or retain heat. For instance, as carbon-rich material sinks and forms diamonds, gravitational energy is released as heat, a process that might occur more vigorously in Neptune. Neptune's interior might also be continually settling and contracting slightly, converting potential energy to thermal energy. In any case, Neptune's interior remains a source of substantial power, while Uranus's is comparatively quiescent. The consequences of this disparity are evident in the two planets' weather. Neptune's abundant internal heat energizes its atmosphere, feeding some of the fastest winds and fiercest storms in the solar system. Uranus, lacking a similar power source, often appears placid and featureless by comparison. For observers of the outer planets, Neptune is the restless one, a blue world with wild weather, whereas Uranus is the calm one, a cyan orb with only occasional stirrings. The hidden heat, or lack thereof, within these ice giants is a key to understanding their personalities. As we leave behind the mystery of Uranus's coolness and Neptune's warmth, we turn to the dramatic expression of Neptune's energy, its roaring winds and wandering storms. Dark, cold, and whipped by supersonic winds, Neptune lies on the edge of the solar system, with an atmosphere as dynamic as it is distant. Although sunlight at Neptune is only 1,000th as bright as at Earth, Neptune's skies churn with some of the fastest air currents ever measured. Jet streams of methane-rich air race around the planet at up to 200 miles per hour, 2,000 kilometers per hour, speeds that dwarf even the most violent hurricanes on Earth. In Neptune's upper atmosphere, where the frigid air is thin, these winds can approach and possibly exceed the local speed of sound, truly earning the description supersonic. The absence of land or obstacles allows Neptune's winds to howl unabated around the globe. Fueled by the planet's internal heat and rapid rotation, Neptune's atmosphere organizes into broad bands and whirling storms, despite receiving only a dim trickle of solar energy. It is a counterintuitive reality. In the far twilight of the sun's reach, this ice giant hosts weather wild enough to rival any world. Neptune's exuberant atmosphere reveals itself in the form of immense dark storms that appear and vanish within a few years. In 1989, NASA's Voyager 2 spacecraft flew past Neptune and discovered a colossal storm system dubbed the Great Dark Spot, a shadowy, oval cyclone as large as the Earth, raging in Neptune's southern hemisphere. A smaller dark spot rotated further south. But when the Hubble Space Telescope observed Neptune in 1994, both of Voyager's dark storms had vanished without a trace. In the years since, Hubble and other telescopes have watched new dark vortices emerge in Neptune's atmosphere, typically at mid or high latitudes, persist for a short time, and then dissipate. Unlike Jupiter's Great Red Spot, which has endured for centuries, Neptune's great spots are transient features. These dark spots are likely gigantic high-pressure systems, comparable to Earth-sized hurricanes turned inside out, high pressure, not low. They often have bright white companion clouds of methane ice, which form as ambient air is forced up over the vortex. Yet even the mightiest of Neptune's storms tend to be short-lived, breaking apart after a few years, as their internal winds can no longer hold them together. It is as if Neptune's storm systems are constantly brewing and dying in a planetary heartbeat. Even when Neptune's storms seem to follow a pattern, this planet of surprises finds ways to astonish us. In 2018, Hubble spotted a new large dark spot in Neptune's northern hemisphere. As months passed, the vortex drifted toward Neptune's equator, where such storms are usually expected to fragment and disappear due to the changing atmospheric conditions. But instead of disintegrating, this dark storm defied predictions. It stopped its equatorward drift and reversed course, drifting back northward away from the equator. Intriguingly, during this U-turn, astronomers observed a smaller dark fragment bud off from the main vortex and take on a life of its own nearby. This smaller dark spot persisted for a brief time before fading, while the original storm continued on. Such an event had never been seen before. It hinted that Neptune's vortices can undergo complex evolutions, perhaps splitting or shedding material as they interact with changing winds. Each new observation of Neptune's restless weather brings more questions. The physics of these far-off storms remains an active subject of research, reminding us that we have much more to learn about the climate of this distant world. What powers Neptune's roaring winds and ephemeral storms? Lacking significant solar warmth, the energy driving Neptune's weather must come from within. Neptune's interior is still releasing heat from its formation, and this warmth rises upward, fueling convective turbulence in the atmosphere. Essentially, Neptune boils from within, and that boiling momentum turns into kinetic energy in the atmosphere, spinning off jets and eddies. The dark storms themselves are believed to draw material up from deeper layers. Their dark hue might indicate they are dredging up compounds that absorb more red sunlight, making them appear dark against Neptune's blue-green clouds. Indeed, when a dark spot rolls through, bright methane ice clouds often appear around it, likely formed by gases cooling and condensing as they surge upwards at the storm's edges. Observations confirm that the cloud tops in a dark vortex reach higher altitudes than the surrounding cloud deck, as if the storm is a powerful chimney lofting materials skyward. Meanwhile, Neptune's rapid 16-hour rotation stretches storms into elongated shapes and confines weather systems into thin latitude bands. And unlike Earth, Neptune has no solid surface to impede or break up storms. A vortex can last until internal dynamics cause it to collapse. All these factors, internal heat, rapid spin, and the freedom of an all-ocean planet, combine to create a perfect arena for supersonic winds and whirling tempests. By comparison, Uranus's atmosphere is eerily quiet, a fact that underscores the role of internal heat. With its meager heat flow, Uranus manages only occasional storms triggered by seasonal sunlight changes. Neptune, in contrast, is a blue cauldron of activity year-round. The fastest winds ever recorded, enormous swirling spots that come and go, and unexpected reversals of storms. Neptune offers a spectacle of dynamic weather in a realm where the sun's influence is but a pale whisper. Standing on the cloud tops of Neptune, if one could, under a dim sun barely distinguishable from other stars, one would still feel the rush of a mighty wind and see the formation of towering dark cyclones. It is a vivid reminder that even at the far frontier of our solar system, the forces of nature continue to operate with breathtaking intensity. Farther out from Neptune's tumultuous skies, both Uranus and Neptune are encircled by delicate rings that are nearly invisible in the darkness. These are not the majestic, gleaming rings of Saturn, but rather faint, narrow bands and arcs of dust and ice that lurk at the edge of perception. Uranus's rings were discovered only in 1977, when observers saw a distant star blink out briefly several times as Uranus passed in front of it. Neptune's rings were similarly elusive, hinted by flickers in starlight and confirmed by Voyager 2 in 1989. In the feeble sunlight so far from the Sun, these rings reflect very little light. Uranus's 13 known rings, for example, are charcoal dark, with ring particles coated in radiation-darkened material that gives them a reflectivity of just a few %. They reside like ghostly hoops in the dusk, visible mainly when they momentarily block starlight or when backlit by the sun. Uranus has a complex of narrow rings that are strikingly confined and thin. The main rings of Uranus are only a few kilometers wide and composed of relatively large particles, centimeters to meters across, with very little dust. They are thought to be the remnants of a shattered moon or moons. Perhaps long ago, Uranus had an extra moon that was broken apart by an impact or torn apart by gravitational forces. The debris from that event could have settled into orbit, gradually spreading into the thin ringlets we see today. Each ring occupies a particular zone around Uranus, where gravitational forces allow particles to cluster and survive. Even so, keeping such narrow rings in line is not simple. Early theories assumed that every thin ring must be herded by small shepherd moons, little moonlets whose gravity corrals ring particles and prevents them from dispersing. Voyager 2's flyby of Uranus in 1986 found only one clear pair of shepherd moons, Cordelia and Ophelia, which flank Uranus's brightest ring, the Epsilon ring, and keep it sharp-edged. Many of Uranus's other rings have no obvious shepherd moons. Their continued existence in such a narrow state is somewhat puzzling. There might be unseen moonlets embedded within these rings, or perhaps gravitational resonances with Uranus's larger moons help corral the ring particles. In any case, Uranus's rings challenge our understanding of ring dynamics, somehow remaining tightly confined over long timescales in defiance of the diffusive tendencies that would normally smear them out. Neptune's rings present a different kind of mystery. When Voyager 2 approached Neptune, it found not complete rings, but peculiar arcs, clumpy segments of a ring, in Neptune's outermost Adam's ring. 4 prominent arcs, given the evocative names Liberté, Égalité, Fraternité, and Courage, were observed. This was puzzling, because basic physics dictates that ring particles should spread evenly around their orbit instead of bunching up. Yet Neptune's ring arcs persisted as distinct clusters, as if held together by some unseen force. The culprit turned out to be a nearby moon. Neptune's small moon Galatea orbits just inside the Adam's ring, and through gravitational resonances, it confines the ring particles into arcs. Galatea effectively herds the Adam's ring material, preventing it from distributing itself uniformly. Thanks to Galatea's shepherding influence, Neptune's arcs remain intact, though they still appear precarious. Neptune's entire ring system is thin, dark, and likely young, probably only tens or hundreds of millions of years old. Without continuous herding by Galatea, and perhaps other unseen moons, the arcs and rings of Neptune would gradually drift into an amorphous band. The very existence of Neptune's confined arcs is a testament to a delicate gravitational balancing act. Both Uranus and Neptune likely gained their rings relatively recently in solar system history, and these rings may not last forever. Cosmic micrometeoroids constantly pelt ring particles, grinding them down into dust that can be blown away by solar radiation. The rings also spread slowly due to particle collisions. In the distant future, the tenuous bands around Uranus and Neptune could dissipate entirely, perhaps vanishing as quietly as they formed. But at the present moment, in the dim outer reaches, both ice giants still wear their subtle adornments. Uranus's narrow rings and Neptune's faint arcs are like whispers of past events. A moon shattered here, a moon shepherding there, frozen in place against the odds. They are nearly invisible relics of the processes that shape planets and moons. In their fragility and persistence, these rings exemplify the balance of forces in the outer solar system. Gravity and chance have conspired to maintain them, however tenuously, reminding us that even in the cold and dark, structure and order can emerge and endure. Neptune's largest moon, Triton, is an oddball that defies the usual patterns of the solar system. It circles Neptune backward, opposite to Neptune's rotation, in a steeply tilted orbit. This retrograde motion immediately flags Triton as a visitor captured by Neptune's gravity, rather than a moon that formed in place. In fact, Triton has more in common with distant Pluto than with Neptune's other moons. It is nearly the same size as Pluto, and likely originated in the Kuiper Belt, the vast region of icy bodies beyond Neptune. At some point eons ago, Triton wandered too close to Neptune and was snared. The outcome was catastrophic for Neptune's original satellites. Triton is so massive, comprising over 99% of the total mass orbiting Neptune, that its capture would have gravitationally wreaked havoc on any smaller moons. Scientists suspect Neptune's original family of regular moons was demolished when Triton barged in. In one fell swoop, Triton turned Neptune's once orderly satellite system into a scene of ruin. The intruder likely flung some moons out of orbit and sent others crashing into Neptune. What remained was a wreckage of debris that may have rained onto Neptune or formed transient rings. Today, Neptune's moon system consists mostly of Triton itself and a few much smaller moons that orbit closer in, essentially a new set of moons that formed after Triton's tumultuous arrival. Triton is now a solitary giant among Neptune's retinue, a moon quite unlike any other in the solar system. Once it was a dwarf planet travelling independently around the Sun. Now it is bound to Neptune, forced into an eternal, circular dance around the planet that captured it. No other large moon orbits opposite the direction of its planet's spin. Triton's backwards, tilted orbit is uniquely bizarre and underscores its captured nature. Over time, Triton's initially chaotic orbit around Neptune became nearly circular, likely as Triton lost energy through tidal interactions and possibly by ploughing through debris left from Neptune's former moons. Today, Triton's orbit is stable and close to Neptune, but it remains retrograde and inclined, forever marking it as a stolen world held captive. Despite being bathed in Neptune's cold shadow, Triton has proven to be surprisingly active. This frigid moon has a surface temperature of about 38 K, 235 degrees. One might expect a world that cold, so far from the Sun, to be geologically dead. But when Voyager 2 flew past Triton in 1989, it found clear evidence that this frozen moon is still alive. Voyager observed dark streaks across Triton's pale pinkish ice, the fallout from active geysers erupting from Triton's surface. In some images, scientists spotted nitrogen gas and dust spewing from ice volcanoes and lofting about 8 kilometers, 5 miles, high. This was a staggering discovery. Triton is one of the few moons known to have active geology, Io and possibly Enceladus being others. It appears that sunlight, weak as it is at Neptune's distance, can penetrate Triton's translucent nitrogen ice cap in the southern hemisphere. That sunlight warms darker material beneath the surface, causing trapped nitrogen gas to build up pressure and burst out through vents, like a cold, faint version of Old Faithful geyser. The venting gas carries darker dust that then settles onto the surface, creating the wind-blown streaks Voyager saw. Aside from these geyser plains, Triton's terrain is a rugged wonderland of exotic ices. Voyager mapped vast plains of frozen nitrogen and methane, a strange cantaloupe terrain of knobbly ridges with no known analogue elsewhere, and polar caps coated with layers of nitrogen and methane ice. Triton even has a tenuous atmosphere, mainly nitrogen like Earth's, but 100,000 times thinner. During Triton's summer, this thin atmosphere slightly thickens and has been observed to warm by a few degrees, a mysterious change possibly related to seasonal evaporation of surface ice. Triton, in short, is a captured moon that manages to be one of the most active and intriguing bodies in the outer solar system. In the far future, Triton's story will take an even more dramatic turn. Because Triton orbits Neptune in the wrong direction, gravitational tides are gradually pulling it inward. With each passing million years, Triton spirals a tiny bit closer to Neptune. In about 3.5 billion years, Triton will reach the point, the Roche limit, where Neptune's gravity overtakes the Moon's own cohesion. At that moment, Neptune will literally rip Triton apart. The once independent world will be torn into countless fragments. Astronomers predict that those fragments will form a spectacular set of rings around Neptune, temporarily giving the distant planet a shining halo to rival Saturn's. The planet that once captured Triton will, in the end, consume it, shattering the Moon into orbiting debris and slowly accreting that material onto Neptune over time. It is a melancholic fate, but also part of a continuing cycle of cosmic evolution. The death of Triton will likely adorn Neptune with a beautiful ring system, a final memorial to the solar system's most wayward moon. In Triton's odd, backward dance and eventual doom, we witness the powerful consequences of gravitational capture and the transient beauty that can arise from stolen moons. Such is the final destiny of Triton, a once free world ultimately undone by the planet that captured it. Beneath the blue clouds and banded atmospheres of the ice giants, hidden from any direct observation, lie interiors of extreme physics and exotic matter. Uranus and Neptune are often called ice giants for their composition, but this term belies the bizarre reality under their clouds. Deep inside each planet, pressures climb to millions of times the atmospheric pressure at Earth's surface, and temperatures reach thousands of degrees. The ices of water, ammonia, and methane that make up most of Uranus and Neptune are not ice at all in those conditions. Instead, these materials form a hot, dense fluid, a global ocean of sorts, that surrounds a compact core of rock and metal. The upper layers of Uranus and Neptune transition from atmosphere to fluid mantle gradually. Under the weight of an entire planet, water and other molecules can break apart and flow in unusual ways. By about 10,000 kilometers down, the environment may be like a supercritical fluid, not exactly liquid or gas, with properties of both. And beyond that, stranger phases are expected to emerge. In the darkness far below the cloud tops, common substances morph into forms found nowhere else on Earth. The environment there may be more alien than anywhere else in the solar system. One of the most captivating predictions is that it could literally rain diamonds within Uranus and Neptune. Decades ago, scientists speculated that carbon deep in these planets might crystallize into diamonds and fall like hail. Now, laboratory experiments have lent credence to this idea. Methane, a major component of the ice giants, is composed of carbon and hydrogen. Far beneath Uranus's and Neptune's clouds, methane is subjected to pressures millions of times higher than on Earth and temperatures of thousands of degrees. Under those conditions, methane's molecular bonds cannot hold. The carbon atoms are liberated, and scientists suspect they might rebind into lattices of diamond. These diamonds would then sink through the fluid interior, raining down toward the core. In 2017, researchers using high-powered lasers at a laboratory in Germany were able to simulate conditions like those 8,000 kilometers inside Neptune. For a fleeting moment, they observed carbon in their plastic proxy material compress into diamond-like structures. This experiment provided direct evidence that diamond formation is plausible in the ice giants. What's more, the scientists calculated that the diamonds in Uranus and Neptune could grow to enormous sizes, perhaps weighing millions of carats. Over countless years, the diamond crystals would slowly drift downward. They could accumulate as a glittering layer around the planet's cores, or dissolve in hotter depths along the way. Imagine an everlasting thunderstorm in the deep darkness, with flashes of crystallizing carbon and a constant glitter of diamonds falling silently into a black sea. It's a stunning image that illustrates just how exotic these distant worlds might be. The extremities of pressure and temperature inside Uranus and Neptune likely produce other strange phases of matter as well. Take water, for example. In the cores of the ice giants, water doesn't remain a simple liquid or solid. Instead, theorists propose it enters a state called superionic ice, a peculiar phase where water's hydrogen and oxygen atoms partially separate. The oxygen atoms fix into a solid crystal lattice, while the hydrogen ions continue moving through that lattice like a liquid. This superionic water would be incredibly hot and dense, as dark as coal and about as hard, yet it would flow internally and conduct electricity almost like a metal. If a layer of this superionic ice exists within Uranus or Neptune, it could help explain a long-standing puzzle: the oddball magnetic fields of these planets. Both Uranus and Neptune have magnetic fields that are highly tilted relative to their rotation axes and offset from the planet centers. Unlike Earth's magnetic field, generated in an aligned iron core, or Jupiter's, from metallic hydrogen deep inside, the ice giants seem to generate magnetism in their intermediate layers. A churning, convecting shell of superionic water could act like a giant dynamo, creating a lopsided magnetic field that emerges at unexpected angles. In effect, what appears to us as calm, pale blue planets might conceal seething inner oceans of conductive, hot ice, driving auroras and radiation belts above their clouds. These speculative glimpses of diamond rain and superionic ice highlight how much we still have to learn about the ice giants' interiors. No spacecraft has yet probed deep into Uranus or Neptune, and our picture of their insides is drawn from gravity measurements, magnetic readings, laboratory simulations, and a lot of educated guesswork. Someday, orbiters or probes might descend through their atmospheres to directly sample these hidden regions. For now, the deep interiors of Uranus and Neptune remain an enigma, likely far more dynamic and complex than we can imagine with current data. The seemingly simple label of ice giant belies a world of extreme chemistry and physics under the hood. Carbon, oxygen, nitrogen, and hydrogen, the building blocks of ices, behave in astonishing ways under crushing gravity, giving rise to shimmering crystal rains, strange new phases of matter, and perhaps other phenomena yet to be conceived. As our journey through the known planets comes to an end, we are reminded that even in what seem like the most distant and inhospitable reaches, nature is endlessly inventive. The enigmas of our solar system continue, and beyond Neptune, in the dim halo of comets and primordial ice, the story is far from over. The voyage now leads us outward into the ultimate frontier of our sun's domain, where even more mysteries await in the darkness.